Hello, everyone, and welcome to this year's annual Muscle Study Group. I'm Rick Barron, and we're going to have some introductory remarks from myself and co-chair Professor Michael Hanna. So please note that this entire meeting will be recorded, and on behalf of the MSG, we'd like to welcome each one of you to this annual meeting. It's a really exciting time in neuromuscular research as we continue to grow and adapt as we develop new understanding about diseases and new therapies. So we once again are conducting our meeting virtually, given the recent surge of COVID over the summer, but we learned from our last meeting that Zoom is a very effective way to communicate as a distance. And I don't think the virtual platform will take away from our meeting at all. If anything, it will enhance it. So again, we've set up the meeting for 3 morning sessions, as all day sessions can contribute to Zoom fatigue syndrome, or ZFS, and our European colleagues need to get some sleep at some point. So we're just going till about noon Central Time. Dr. Hanna, Professor Hanna from London, Queen Square, why don't you take this slide?
Great. So I also like to add my welcome to everybody. It's great to be back at the MSG. So the goals of the MSG are listed here. We want to be the premier organization, an annual meeting for neuromuscular clinical trials. As you know, we particularly want to support and develop young investigators in the field. That's a high priority for us. We are focused on fostering international collaboration, often necessary for the trials we need to do. And we also work hard to connect to preclinical colleagues who are exploring potential pathways for new treatments for neuromuscular disease. And that's clearly really exciting at the moment. And a really high priority for us is to work closely and engage with partners in industry. Next slide. So me and Rick want to give a huge thank you to the colleagues listed here. Not me and him, the rest of them who did all the work in planning this meeting. I think it's a fantastic program. They had to pivot from, was this going to be a face-to-face meeting or a virtual meeting? So they did a lot of work, and we really just want to thank them for everything. And I think it's a great program. Over to you, Rick.
All right. Well, as Michael alluded to, we have industry partners, and industry participation is a huge key for our successful MSG meeting. And we can't do this without the financial support of our many sponsors. So we're proud to mention that our platinum sponsors are CSL Behring and Dyne Therapeutics. And our next slide, our gold sponsors, here we are Arginex, Genentech, and PTC Therapeutics, all of which you'll be hearing from over these next few days. Next slide. We also want to thank our silver sponsors, Biogen, Sarepta, and UCB. Thank you very much. And our corporate sponsors. We really want to thank our corporate sponsors, Alexion, Amylyx Pharmaceuticals, Audentes Therapeutics, Catalyst Pharmaceuticals, Kaba Fusion, New Factor, Optum Specialty and Infusion Pharmacy, Solio Health, and Spark Therapeutics. Thank all of our sponsors very, very much. Back to you, Michael.
Thanks. And we also want to just really thank the MSG Executive Committee who have worked hard over this past year. They're listed here. We're grateful to all of them for the work they've done in helping us with our strategic direction, advising us in relation to the annual meeting, assessing protocols for studies to be granted as MSG studies. So the executive is a crucial part of the MSG, and we're really grateful for all the work they've done over this past year. So thank you to them. And back to you, Rick.
Yeah, and Michael and I want to give a big personal thank you. Yeah, go to the next slide, please, to folks on this slide. So Liz Polk, who many of you know through virtually, and some of you met her in person in prior meetings. She is the heart and soul of this. I cannot tell you how hard she works to get this meeting together. Thank you, Liz. That's Liz there. And then my new best friend, Amardeep Gill from Staten Island, is our stream guru. He is amazing in getting us ready for these meetings. Also at the University of Kansas, research coordinators Kelly Higgs and Michaela Walker have been crucial to help Liz get this all together. Now, next slide. So the executive committee in this last year made the new RRNMF Neuromuscular Journal the official journal for the MSG. And so all the abstracts from this meeting have been published already in the September issue of the journal. So please sign up to the journal to receive it free. And when you do that, sign up to become a reviewer if you want. Put in the areas of articles you want to review. Please submit articles. And if you want to be part of the editorial team, what I call a facilitator team, please contact me. It's a volunteer group. I particularly want, to get women and minorities involved in the facilitator group process. So please contact me. Next slide. So with some meeting housekeeping, virtual housekeeping, figure out where your bathroom is, figure out where you can get refreshments. And I have coffee, so I'm good. So make sure you got coffee. Michael's got coffee. And Dr. Hannah, I think you got the last slide.
Yeah, so this is just some general meeting information for everybody. If you'd like to ask a question, click on the raised hand icon in the reactions tab, and the facilitator will allow you to speak or type your question in the chat, and the moderator will read your question. The mingling sessions are important, and they'll be at the conclusion of each day's session. You'll be able to go from room to room, and it's an opportunity to try and network a little bit and meet colleagues from different areas, fellows and industry insiders. So I would strongly advise you to not just end at the end of the meeting, but go into the mingling rooms. CME will be offered for this meeting. The information about how to obtain CME will be sent out very soon. So I hope you enjoy the meeting, and back to you, Rick.
Yeah, and chat. I'm just sending a welcome chat to everyone. So last year we didn't have chat because we were doing it streaming. It was I don't know. Technically it was different. This year we've got regular Zoom chatting. So, all right. So we're already a few minutes behind. And you're good. The talk that Michael and I used to give for 20 minutes, we divided up over the next 3 days. So we'll hear more about the MSG tomorrow and Sunday. We need to launch right into the annual Robert C. Griggs MSG lecture, which is named in honor of the founder, the inspiration, the godfather of the MSG, Dr. Griggs. And we are so pleased, and there he is. Hello, Dr. Griggs. Good morning.
Good morning, Dr. Barron and Dr. Hannah.
Yes. Thank you. Thank you. We've already got almost 100 people logged in, and I know we've got over 300 registered, so we're doing well. All right, so we are so pleased this year to have as our Robert C. Griggs annual MSG lecturer, Dr. Gordon Smith, who's professor and chairman of the Department of Neurology at Virginia Commonwealth University, where he serves as the Kenneth and Diane Wright Distinguished Chair in Clinical and Translational Research in Neurology. So Dr. Smith, as many of you know, is a graduate of University of Virginia undergrad, Mayo Medical School. Then he did residency in Michigan. And he's an internationally recognized expert in neuromuscular medicine with a particular focus on peripheral neuropathy. Prior to being at VCU, he was at University of Utah, where he was the director of the Jack H. Pettijohn EMG lab, and he had a number of leadership roles. Dr. Smith's NIH-funded research team focuses on peripheral neuropathy and diabetes and obesity. He's particular interest in biomarker development and novel clinical trial designs in neuropathy. He was principal investigator of NeuroNext at Utah, and he still is the PI of a really important NeuroNext study of topiramate for C-SPAN, which I think we'll hear about during his talk. Dr. Smith is also the PI of the Activity for Diabetic Neuropathy ADAPT study, and he's very interested in impaired glucose tolerance and the metabolic syndrome and how it relates to neuropathy. So we are so pleased to have Dr. Smith as this year's Robert C. Griggs lecturer, and so I won't take any of your time. Dr. Smith, I'm going to turn it over to you.
Rick, thanks for that great introduction. Let me pull up my slides here. Thank you so much for the invitation. I have to say, when I first got the invitation, I thought this must be a joke. I'm so honored by it. And I was telling colleagues this morning on a Zoom before this, I haven't been nervous about a talk in, I don't know, forever, but the idea of giving the Robert Griggs lecture at the MSG with Birch looking at me is a little anxiety provoking. So Birch, I hope I stand up to your high standards in this talk. So here are my slides. And really what I want to do is summarize a lot of work by a lot of people over a period of time and challenge some of our concepts surrounding idiopathic and cryptogenic neuropathy and really focus on therapeutic development, because I think that we are entering a phase where there's, I think, real hope for our therapeutic pipeline. So I want to start by just getting into my disclosures, I suppose. So I will be talking about work that has been funded by NIDDK and NINDS, as well as the American Diabetes Association. I'll talk about skin biopsy. I don't have any kind of financial conflicts of interest with the Utah laboratory now, except that I refer to them. And this is where we do our research sample processing. So I do want to start with, it maybe seemed like a fine point, but idiopathic and cryptogenic mean different things. And this is a really great quote from a article that talks about this concept in the setting of idiopathic pulmonary fibrosis. And it turns out the word idiopathic really comes from ancient Greek. Idios meaning one's own or particular to an individual, and pathos meaning suffering, which is different from cryptogenic, which means hidden origin. And so as much as I like C-SPAN, I'm going to point out throughout this talk that I think our concept of idiopathic neuropathy needs to move beyond the I don't know, perhaps into one's own particular disease. But certainly I think we've understood a lot more over the past decade or two regarding what idiopathic neuropathy really means. And I'm going to frame this discussion in a series of questions. I know this is a muscle study group, and so I feel obligated to explain, just in case, why does neuropathy matter? Why is this important? First of all, it's incredibly common. This are data from the Dutch group. And as you can see, by the time individuals are in their 80s, almost half have some evidence of neuropathy. They have possible neuropathy. And if one considers probable or definite neuropathy, definite being neurophysiologically confirmed neuropathy, it's about a third. And so all told, in adults over the age of 50, probably around 8% have neuropathy. So this makes it one of the most common neurological problems. And it's deceptively disabling. You may not notice it disabling the person sitting across the table from you, but it can be because of neuropathic pain, foot ulceration, amputation, particularly in diabetes, and fall-related injury. And I think what's often underappreciated are the central nervous system manifestations. There's actually really interesting literature regarding neuropathic pain and CNS mechanisms. But here I'm really talking about reduced quality of life in the setting of depression and anxiety. There's a 50% relative increase in the risk of depression and anxiety in both diabetic and cryptogenic neuropathy. Those who have diabetic neuropathy have a 50% risk of having either depression or anxiety, and a quarter have both. And not surprisingly, the main predictor of these outcomes are pain and gait instability. And so while the core manifestations, the disabilities we as neuromuscular neurologists think about are the drivers, these drivers lead to downstream CNS and behavioral manifestations that can be quite disturbing. And unfortunately, right now in axonal neuropathies, the therapeutic landscape isn't very broad. So for symptom management of distal symmetric polyneuropathy, unless I'm missing something, which is certainly possible, there are really only 4 FDA-approved drugs. So pregabalin, duloxetine, tapentadol, and then high-dose capsaicin. Obviously, other drugs that we use off-label. Really 2 disease-modifying therapies for axonal neuropathies, both for hereditary amyloidosis. Very exciting, innovative drugs, but nothing in the space of diabetic neuropathy or cryptogenic neuropathy. And there have really been, before the topiramate trial, which I'll talk about at the end, no randomized controlled trials that target disease modification in C-SPAN or idiopathic neuropathy. And so that's where we're starting from, but I think it's better than this seems, as I'll get to. So before we get into therapeutic development, think it's helpful to think about classification and measurement, which may not seem like they're important, but they really are. And I was reminded of this just in clinic the other day, of this story, which I like to tell. So I'm not a headache doctor, but I am familiar with the concept that headache has become a really exciting therapeutic field. And I think this was really driven by the classification work done by the International Headache Society. So I have a patient who has a neurofascian-mediated neuropathy who has nocturnal headaches, which I learned from this classification system are called hypnic headaches, and there are specific treatments that one uses for hypnic headaches. And when I was a resident, these would have probably been studied as migraine headaches. And we really need the same sort of approach in neuropathy. And it's particularly hard in axonal neuropathies because different causes look a lot like each other. So we need to do this work, and it's going on. And I'll give you an example of why we need to do it. And one of the strangest studies I ever did, Peter Dick, who you can see over here, brought together a group of experts in diabetic neuropathy to Rochester about 10 years ago. And we were asked to examine randomly selected patients from the Rochester diabetic neuropathy cohort who were disguised. And so this is the disguised patients, and you'll see we're all wearing headphones for voice distortion. So Peter's very thorough. And all we had to do in the Kaler Hotel was to go from cubicle to cubicle and decide whether the particular patient in front of us had neuropathy. We came back the next day, did the same thing. That at this point they were no longer disguised. So we saw what they looked like and listened to what they heard like. Or heard what they sounded like, and this is the result, and it was rather sobering. So, the left here, you see the number of times each of the 12 experts agreed with Peter regarding the diagnosis, which was really not Peter's personal opinion. It was based on neurophysiologic criteria. Doesn't matter whether you agree with those criteria, but you'll see that some of us agreed with Peter 20 times, some of us only agreed with Peter 12 or 13 times. So lots of inter-observer reliability issues. But more striking, when we came back the next day, you'll see over here in the Kappa statistics that a quarter of us didn't even have a statistically significant relationship between what we thought one day versus the next. So this was a bit discouraging. It did buy us all a return trip to Rochester, Minnesota in December the next year with a foot of snow to repeat the study, which we did and agreed on our diagnostic criteria, and this improved a lot. And so a good example of why we need to use structured criteria and classification systems, something that clearly comes out in our trial design work. And this effort is really being led by a colleague of Dr. Griggs at the University of Rochester, Bob Dworkin, who's a pain psychologist and a clinical trial expert. And this is through the framework of ACTION. You can read what ACTION stands for there. It's a long title, but basically ACTION is a public-private partnership with the FDA, includes other governmental entities. You'll see the logos below, with the idea that we can do better to improve clinical trials and expedite discovery of therapies, not only for pain, but specifically for peripheral neuropathy. And ACTION has a number of subgroups, all with similarly complicated names like IMPACT and CONCEPT. And these are the groups that are focused on neuropathy. And that work is now really leading us to a more nuanced view of diagnostic criteria. So this is an ACTION impact paper that was published just about a year ago, where we crafted criteria for idiopathic distal sensory polyneuropathy. And these, I think, are really just scratching the surface of what we need to do. I'm not going to go through the details in the interest of time, but suffice it to say, there's this framework now for people who are interested in doing trials in one specific type of neuropathy. And you'll see that these really coalesce around fiber type involvement, which is a key concept. That peripheral nerves are complicated and involve multiple different fiber classes. And we're all familiar with this concept of large myelinated fibers controlling strength and subserving proprioceptive function, where unmyelinated or lightly myelinated fibers pain, autonomic function. And there are different tests that we use to diagnose these. And this, of course, means different tools we might use to measure them. And it's worth thinking about the biologic implications of this. So this is a picture of Theodore Schwann. He's got a nice bow tie on, and we see the cell that bears his name on the right. And of course, the Schwann cells are responsible for myelinating large diameter axons, and this enveloping myelin sheath facilitates saltatory conduction, high high conduction velocity, also provide some protective barrier for axons. And so this is great. They're fast, they're relatively protected. There's a cost though, because if there is axonal injury, the process and mechanism of axonal regeneration for myelinated axons is challenging. This is a complicated structure to recapitulate. This all stands in contrast to unmyelinated axons. These are supported by a different cell. It's not usually called a Schwann cell, although it is in this electron micrograph. It's called a Remack cell, and this is a picture of Robert Remack on the left, who's an interesting guy. He was actually a contemporary of Theodore Schwann. And these unmyelinated axons are slow, so their conduction velocities are in the single meters per second, and they are actually quite prone to injury. But they're also uniquely capable of regenerating. And therefore, it is likely that the reason we even have these slow, fragile fibers is because of this regenerative capacity. And these are concepts that Jack Griffin really first introduced now quite some time ago. And that is that in a peripheral environment where there's high degenerative pressure, so the most distal portion of the peripheral nervous system in the skin, unmyelinated axons are desirable because they can rapidly regenerate. And in fact, these axons are continuously degenerating, regenerating within the skin. An example of why this is probably true is that on the right, you'll see an EM from the brain. And in most regions in the brain, small diameter axons are actually myelinated in distinction to the peripheral nervous system. We certainly hope within our brains that we don't have ongoing axonal degeneration, whereas in the peripheral nervous system, it's part of our daily lives. And so how do we measure these fibers? And really, there's two tests that we use both clinically and that are commonly used in clinical trials. And nerve conduction studies on the left measure large myelinated fibers, and here we see a skin biopsy being performed. This is stained with PGP 9.5, and you can see in a normal individual, robust innervation up in the epidermis, and in someone who has neuropathy, we see simplification. So that actually interesting biology of skin as a sensory organ, but there's simplification of the structure of the skin, and those fibers are absent. And we and others have found that this is a particularly sensitive measure of early neuropathy. So these are data from the Utah Diabetic Neuropathy Study looking at patients who have early neuropathy and diabetes within 5 years of symptom onset. And what we see is less than half of those who have definite neuropathy, and I'm happy in the questions if you're interested to define how we did that, had abnormalities in nerve conduction studies, whereas almost 80% had abnormalities on skin biopsy and 70% of QSART, a measure of pseudomotor function. And so it seems that in these patients, measures of small fiber function are abnormal earliest in the disease. That doesn't necessarily mean that it's small fiber onset. It just means these are more sensitive measures. What's more, they're responsive. And so this is the same data set over a 2-year period. And you can see that over 2 years, there's statistically significant, very clear progression in epidermal nerve fiber loss. There's reduction in sweat volume with QSART. There's worsening of cold detection threshold, and yet measures of large fiber function remain stable. And what's striking, of course, is the FDA for axonal neuropathy trials is still focused on nerve conduction velocity as a preferred surrogate measure of neuropathy severity. And I think most of us would agree this is probably not the most clinically meaningful outcome. We certainly have seen drugs that do well at this. Aldose reductase inhibitors, for instance, improve nerve conduction velocity, but they don't result in a clinically meaningful difference for patients. As an aside, there are other ways we might look at these small diameter axons, and one is in the eye. This is not a biopsy. This is a pathology section from an autopsy of the cornea. It looks a little bit like skin, and in the schematic, you can see that there's Bowman's layer, so a nerve fiber layer underneath the epithelial layer, very much like skin. And we can image this in human beings, actually in animal models as well, using a confocal microscope. And so this is a picture of a neuro-ophthalmology fellow, gamely serving as a normal subject. And you can see the applanation of the eye here. There's a camera on the side, and you can see the nerve fibers here. These are videos of the images being acquired, and on the right, the imager is holding the nerve fiber in plane. You can see that there's a little compression artifact here, and on the left, scanning from the epithelial layer, which you'll see in a second, through the nerve fiber layer there and into the stromal layer. And it turns out that this shows the same axonal degeneration that we see in the periphery, which is fascinating, right? Because these are really short nerves, whereas we think of neuropathy affecting long nerves, which is an interesting concept to chew on. We see the same progression from control diabetes, diabetic neuropathy, and nerve fiber density and epidermal nerve fiber density. And we even see proliferation of these dendritic cells on corneal confocal imaging. I'm not going to talk more about it. That could be a whole talk in and of itself. I think this is a promising research tool, not ready for a clinical prime time. And when one looks at its relationship with clinically meaningful outcome measures, probably doesn't give us the same type of information as skin biopsy, but it's an interesting concept. So with that sort of housekeeping aside, let's get into the meat of it and talk about the concepts of metabolic syndrome, obesity, and prediabetes, and what this means for peripheral neuropathy, in particular idiopathic neuropathy. Of course, there is a epidemic worldwide of diabetes. Here you see the growth between 2013 and projected 2035. I think a key point here is not only that this is an epidemic, I think you all know that, but that is disproportionately affecting developing countries. So, and it's of course affecting us as well. So as we think about therapeutic approaches, sure, it would be great to have a molecular therapy for diabetic neuropathy or a gene therapy, and people are looking at these sorts of strategies, but that's going to be hard to scale across 600 million people, half of whom have neuropathy worldwide. We really ought to be thinking about scalable, cost-effective, pragmatic therapies. And this epidemic is being driven by obesity. This is type 2 diabetes, of course, and you can see by 2030, most of the United States is projected to have obesity rates of over 50%. So this is a huge public health problem. And as I'll get to, a core concept is, as we're thinking about neuropathy, we really need to think about the biology of obesity. Before patients become diabetic, they often become pre-diabetic. And if diabetes is an epidemic, this is a tsunami. Over 90 million Americans, 1 in 3 adults have pre-diabetes. And many have shown over time that metabolic syndrome and aspects of metabolic syndrome other than diabetes are neuropathy risk factors. And so this is from the Utah Diabetic Neuropathy Cohort, looking at non-diabetes measures. And you can see obesity, hypertriglyceridemia, the metabolic syndrome itself confer a four-fold risk in having neuropathy. And we see this in idiopathic neuropathy as well. Here I'll show some others' data, but it mirrors ours, which is in cryptogenic neuropathy. There's a doubling of the prevalence of metabolic syndrome. And if one looks at the individual components, you'll see the one that really sticks out, to my mind, is obesity. Twofold increase in the risk of having obesity if you have painful neuropathy, and about the same if you have non-painful neuropathy. These are, of course, biased cohorts because you're looking at neuropathy. But if you look at free-range human beings, this is from the CORA study, Dan Ziegler's work in Dresden, you'll see that as we move from individuals who have normal glycemia to diabetes, there's an increasing prevalence of neuropathy, and interestingly, preferentially painful. Now, this may, you'd think maybe this is an acquisition issue, but these are screened patients. And so this is a biological phenomenon, perhaps it's early small fiber injury. And I want you to remember this because I'm going to get into causality and how we determine what causes a disease. And it's really the thresholds for diabetic diagnosis were based on this dramatic increase. But we've known since the 70s that pre-diabetic levels of glucose dysregulation are associated with less significant increases in neuropathy risk. So an important concept. And we see this in obesity as well. And so this is the first data from a study that we did funded by the ADA looking at neuropathy risk in bariatric surgery candidates. And these were individuals who did not have clinically overt neuropathy, but you'll see that they had a very high prevalence of subtle abnormalities, I apologize, on the Michigan Neuropathy Screening Instrument, so a symptom inventory. And they often had subtle abnormalities on the Utah Neuropathy Scale. And here you see the histogram of the prevalence of different scores. And I'll come back to this and talk a little bit about what happens after bariatric surgery, which is really interesting. My only real mechanism slide is here to point out that the mechanisms between type 1 and type 2 diabetes are different but overlapping, and they converge on a shared final common pathways, including mitochondrial dysfunction, inflammation, ER stress, and so forth. And I really want to use this as a launching point and perhaps a plea to use our clinical trials and our human subject studies to try to understand mechanism. And we can do this through both thoughtful clinical phenotyping and biosampling. This is not from one of our trials. This is actually a diabetic mouse on the right and a control mouse on the left, and you can see that these mitochondria look larger and they're more clumpy in the diabetic mouse. And this is something that you see in cell culture as well. This is a DRG explant model, and on the bottom you can see mitochondrial volume in control media and high glucose media, and in the diabetic media, we see the same sort of size distribution change. And one can actually look at mitochondria if you're really motivated and are a bit of a glutton for punishment using confocal imaging of skin biopsies. And this is work we did with the imaging group at the University of Michigan. And you can see the mitochondria measure the same volume data that I've shown you now on the left from cell culture. And this is what we see in patients who have diabetes and diabetic neuropathy, and it replicates the same mitochondrial structural abnormalities. And so file that away. I'm not going to talk a lot more or at all more about mitochondria, except to show you what happens after intervention later on. But really, this is the launching point to talk about therapeutics. And unfortunately, as I alluded to now, the state of the art for therapeutics for diabetic neuropathy is glycemic control. And so for those of you who are interested in the history of medicine, this is one of Banting and Best's first files of insulin on the left and an early type 1 patient. Very interesting story about the race to develop and prepare insulin for therapeutic use. And we've known now since really the DCCT quite some time ago that intensive glycemic control is effective in type 1 diabetes at reducing neuropathy risk and slowing progression. These slides are data from a really great Cochrane review by Brian Callahan, and the DCCT has circled a very large study and interesting in so many ways that I'm not going to get into right now. But what I want to highlight is that this is very different from type 2 diabetes. So very large studies, the Accord trial on the very bottom, over 10,000 patients, have failed to show a significant benefit in aggressive or intensive glycemic control and reducing neuropathy risk. And to put this into numbers that are digestible, the relative risk reduction with aggressive glycemic control in type 1 diabetes is 80%, 5 to 9% in type 2 diabetes. So clearly important. I don't think any of us would say that an A1C of 13 isn't going to make you more likely to have neuropathy or neuropathic problems, but aggressive glycemic control isn't the answer to type 2 diabetes in terms of neuropathy. And so this leads to the obvious question: is metabolic syndrome important? What's the role of obesity, and can these be effectively treated? And this is really where my research career got off the ground, was asking this question. As a fellow working with Eva Feldman in Michigan and with Rob Singleton, we, and I think everyone else at the time, was observing that our neuropathy patients who didn't have diabetes, they looked diabetic. They'd come to clinic, you say, gosh, this person's going to have diabetes, and they didn't. And we started looking, and a very high percentage of them had prediabetes. So we were interested in studying this with the naive concept, maybe if diabetic neuropathy is hard to fix, pre-diabetic neuropathy will be easier to fix. And so we were writing an R01 at the time to do essentially a natural history or clinometric trial. And right before the last submission, and I think this is a cautionary tale that sometimes it's good to not have your first submission funded. The diabetes prevention program was published, and the DPP randomized patients with impaired glucose tolerance to placebo, metformin, or lifestyle, and was stopped early because lifestyle was superior. If we'd been funded on our first attempt, I don't know what I'd be talking about today, but it'd probably be something different. And what we found, interestingly, in the study that was done at Yale, Michigan, and Utah, was that there was clinical improvement and reinnervation in this cohort over a 1-year period. And so the top shows the epidermal nerve fiber density, the left a characteristic image, and the bottom shows that for patients who were able to actually exercise, improve their fitness measured by 6-minute walk, they had improvement in neuropathic pain. I'll show you the long-term outcomes in a moment, but this was pretty exciting to us, and we thought that perhaps we can deploy this in a proof of concept prevention trial. And so we did so in the second phase of the Utah diabetic neuropathy study. I'm skipping over a fair bit of work in between the two, but this trial randomized patients with diabetes who didn't have neuropathy to standard of care community-based treatment or supervised exercise and dietary counseling, very much like that which we used in the IGT study. And the most expensive slide I have, this is years of work and a major R01. What we found is, in fact, this did work, that there was a regeneration of epidermal nerve fibers in those in the exercise group and stability in the control group who received just general counseling. And we know, and Dr. Polydefkis has also shown that in this population, you generally see about a fiber per millimeter decline every year. And here we saw stability. So this is pretty exciting. And as we thought about it, how can we understand mechanism? And I started by saying that these nerves are constantly regenerating. And this is a picture of that. This isn't a GAP43 stain. This is actually STMN2, which I thought would be kind of interesting to this audience because it's obviously relevant to ALS, but it stains regenerating axons. And these nerves are constantly degenerating and regenerating. And therefore, one can think of particularly small fiber neuropathy as an imbalance between regenerative capacity and degenerative pressures, right? It's sort of, is the environment overwhelming Jack Griffin's foot soldiers of the peripheral nervous system? So we can dissect this out actually using a capsaicin axotomy model. And I think everyone's familiar with the concept that capsaicin at lower doses, brief exposure, stimulates TRPV1 nociceptive axons, and in fact is why our chili peppers are hot. But in higher doses or prolonged exposure, it actually causes degeneration, and we see that at the bottom. And what Michael Polydefkis piloted that was really neat was you can then do serial skin biopsies and measure the rate of recovery. And so the red line is the regeneration rate in controls, green diabetes, blue diabetic neuropathy. So we use a somewhat different regeneration model than this, but same concept and a different study paradigm than it's been used before. And that is to do a within group comparison before and after a lifestyle intervention. And so here we see the percentage of baseline fiber density 48 hours after patch placement. And then 30 days later, in a group of patients who have metabolic syndrome, some had diabetes, some did not. These individuals then underwent a year of a lifestyle intervention, after which we repeated the same experiment. And you can see that there was a significant improvement in regeneration capacity, or here it's calculated as a regeneration rate. And interestingly, the likelihood that an individual study participant realized a significant improvement in reinnervation rate was seemed to be predicted by their metabolic success. So those who improved across all of their metabolic syndrome criteria were much more likely than those who improved, for instance, across none of the criteria. So this is interesting and suggests that that the impact of lifestyle interventions may be more on the regenerative side. That doesn't mean there couldn't be a neuroprotective effect, but clearly helping nerve regeneration. So that's interesting and encouraging. But the bad news is these sort of approaches are hard. And one reason they're hard is they're hard to sustain, but there may be some concepts in here that regarding obesity that we need to think about in terms of disease mechanism. This shows the small fiber measures here, 1 year improvement, this is sweat, and then they start to progress again. And you can even see after a year or so that other large fiber measures seem to accelerate a little bit in their decline. And this is despite maintaining weight loss, about a 5% weight loss, which is interesting. And so clearly lifestyle, while helpful in and of itself, is probably not going to be the long-term solution. So our next thought was, well, I think we've all heard the sitting is the new smoking. 10% of premature deaths in the United States are attributable to tobacco use. About the same can be attributable to sedentary lifestyle. And this infographic even gives us some motivation that if we were to cut the inactivity by 25%, we could save 1 million lives. and points out that deaths associated with inactivity are not just cardiovascular, it's actually cancer as well. So the traditional concept of obesity is that of a energetic imbalance, that you're taking in more energy that you're expending. And if that's relevant, then it's important to think about how we expend our energy. And it turns out that the vast majority of our energy expenditure, even for people who run, is in non-exercise activity. Now, I know Birch runs like 50 miles or 100 miles, so Birch is probably able to manage his energy balance with his running. But for those of us who only run 5 miles a day, you probably get more energetic benefit from taking the stairs and getting up and walking around now and again. Not that there aren't other benefits of exercise, but the idea here is maybe we can target inactivity simultaneously. Just some statistics that highlight the mortality risk of inactivity. Here we see on the left risk of cardiovascular myocardial infarction or mortality in older adults related to tertiles of physical activity. I think those speak for themselves. The figure on the right is something you can show your children, which is your risk of mortality. If you watch TV 6 hours a day or more, is about twice than if you don't watch TV. So if you've heard your TV is killing you, that is right. It is killing you if you sit and watch it. So if you're watching it, I would recommend at least get up now and again and walk around or hop on the treadmill. We can measure activity, of course, and there's a robust science in actigraphy. And the way we're measuring this is perhaps not the way we would measure it now with the explosion in biowearables, but this is using a tool that I'll show you in a second called ActivePal that allows us to measure whether or not someone is sitting or lying down, standing or stepping, so walking or running. And so it gives you posture and activity, and you can also calculate the projected metabolic impact of this. And so we piloted using this as a strategy to change behavior in diabetic neuropathy in a small group of patients wearing an ActivePal, which you can program to buzz if the participant's been sitting for 20 minutes. We measured activity and steps before intervention. We then deployed the fibrotactile feedback, and you can see that there was improvement in mean awake time, active, and then steps per day, and that this was durable over a 2-month period after stopping the vibrotactile feedback. And so this is a trial that we're doing with Dr. Barron's former colleagues they're still his colleagues at the University of Kansas, just finishing up Activity for Diabetic Peripheral Neuropathy, where we're looking at the impact of a combined lower intensity supervised exercise, more of a focus on training people to exercise at home, and actigraphy-based counseling for sedentary behavior using vibrotactile feedback in the treatment group. I think what's interesting about this study is I think for the first time, we are looking with intent at the mediation between the intervention and the outcome, which you have to in exercise because people feel better when they exercise. And our primary outcomes are skin biopsy and a quality of life measure. But it may be that exercise just makes people happy, and that's why their quality of life would get better. But it may be that this is mediated through impact on pain, sensory loss. Maybe it's impacted through axonal health, which we measure with epidermal nerve fiber density, maybe gait and balance. The same analysis can be used to look at the meaning of nerve conduction studies, for instance. And so I don't know what this will look like. I'm a little worried the trial might be negative. It's hard to tell because we obviously haven't unblinded things, but be that as it may, it's certainly going to be informative. I think these are strategies you can use now, of course. There are biowearables, your iPhone, Fitbits, and whatnot. And this does have, I think, impact. And so this is actually from Brian Callahan and Eva Feldman. I don't know why they made a video of it. I think they're just showing off. But this shows mitochondrial imaging in an obese patient after a lifestyle intervention. And you'll just have to take it on my word, and I'm taking it on Eva and Brian's word, that there's been a normalization of the mitochondrial abnormalities. And and Brian actually is now looking at the impact of bariatric surgery. And what's interesting is we do see after bariatric surgery in patients who don't yet have neuropathy, significant improvement in subtle evidence of symptomatic neuropathy, which we see over here in the change in the MNSI. And over here, these are baseline skin biopsy for each participant before and after surgery. And there is a slight increase in epidermal nerve fiber density. But these are the individual individual participants' regeneration curve from a capsaicin exotomy experiment. And what you see is that there's no improvement. Yet these patients have significant changes in subtle findings of neuropathy. They have unbelievable metabolic changes. And so the different strategies we use to address obesity, whether it's lifestyle, bariatric surgery, have different biological effects. Not surprising, but this has implications regarding therapeutic targets. And clearly, there's work for translational science in this space to understand disease mechanisms. So I've talked a lot about obesity. Does obesity cause neuropathy? And what are the implications of this answer? I began my career trying to convince people that impaired glucose tolerance was relevant for neuropathy. We couldn't get anything published. And now we're in a phase where people say, of course, it causes neuropathy, which I think is probably not the answer. And I'll tell you what my answer is now, even before we start, which is I've evolved to think of obesity and neuropathy and prediabetes and neuropathy, and for that matter, diabetes and neuropathy, the same way our stroke colleagues think of these vascular risk factors. When a patient comes within a large vessel stroke due to a carotid atherosclerotic event, and they're diabetic and hypertensive, we don't argue whether it's the hypertension or the diabetes. We recognize that these are both important risk factors. And so I tell my patients that the nerves are basically a sensitive barometer of cardiovascular risk. We know that they're relevant risk factors, and cause is, a messy term. But let's talk about it because I think it's important and it has implications. And one way of thinking about cause is through the Bradford-Hill criteria. For those of you who do any toxic neuropathy work, you're very familiar with Bradford-Hill, who is most famous for linking smoking and cancer risk. He sports a bow tie, so I like him. And I think he would say that these viewpoints should not be used rigidly as criteria. And as I go through them, for those of you who aren't familiar, you'll see that it's easy to poke holes in them. But as a body of viewpoints, they certainly inform the relationship between exposure and a disease. And so let's go through them with an eye towards obesity. And so the first of these is strength of association. And we think of that as clinical researchers in terms of effect size and statistical significance. So the larger the effect size in a study looking at hyperglycemia and neuropathy and the greater statistical significance, the more likely we are to conclude that diabetes causes neuropathy. And I've shown you data, and in aggregate, and there's some data that Brian has in press now, 4 to 9 times risk of developing neuropathy and significant obesity. Consistency, do multiple studies using different methodology and different populations show the same relationship, which I think I've hopefully convinced you we see in neuropathy. What about specificity? And the classic example of this is scrotal cancer and chimney sweeps, so Percival Pott. This was a very specific industrial exposure. I don't know how much scrotal cancer you see. I don't know that I've ever seen a patient with scrotal cancer, and I don't think I've ever met a chimney sweep, but chimney sweeps were very specifically at risk for this disease. Now, neuropathy, we can't prove specificity because there's a lot of things that cause neuropathy, and it looks pretty much the same for many of them. So this is one that we can't demonstrate. Temporality, common sense. If a toxic or other health exposure causes an outcome, the exposure needs to come before the outcome. Biological gradient, ideally a dose response effect of some kind. Important to keep in mind that there's so many other variables that it's not necessarily a linear dose response effect. We certainly, I think, see this in hyperglycemia. Remember the figure I asked you to remember. I don't know for certain yet whether we see it in obesity, but clearly morbidly obese patients have a very high risk of subtle neuropathy, and this probably supports this biological gradient. Criteria 6 and 7 are related, which is biological plausibility and coherence across different sources. And here I think it's definitely the case that we see this risk relationship in humans. We have animal models of it, and actually these models suggest shared mechanisms with diabetes, which I'll get to in a moment. And the last 2 criteria are experiments. So if you remove or treat the putative cause, it should lower the disease risk. If you tell people stop smoking, they should have a lower risk of having lung cancer. And I would posit that the work I've shown you suggests that if we address metabolic abnormalities in non-diabetic patients, we do see outcomes. And so I think this is true in humans, certainly true in animals. And then lastly, analogy. If there's strong evidence linking a causative agent with a disease, that supports a causal relationship for a similar agent with weaker evidence. And here, the obvious comparison is diabetes. No one would argue that there's not a relationship between diabetes and neuropathy. And the relationship to really the driver of diabetes and as obesity is pretty simple. And so I would argue that these criteria or viewpoints have largely been fulfilled. I've already said that I don't tell people that their obesity caused their neuropathy, but I do think obesity is mechanistically important in the cause of neuropathy. I think it is really important to challenge our concepts of obesity. And it turns out that as I was preparing for this talk, a new study was published in the obesity literature, which is really interesting. And so the references on the bottom of this slide, I'll tell you a little bit about it. And then if you're not interested in reading metabolic literature, I've got something you can read that summarizes it in a, I would say, neuromuscular friendly way. But the traditional concept of obesity is of an energy imbalance disorder. There are a significant subset of obesity investigators that believe that it is not that. That is a constitutional or hormonal disorder. And in fact, if you go back to the original discovery of the OB mouse, leptin deficient mouse, this actually demonstrates the point, because these mice actually develop obesity even if they have a calorie restricted diet. And so the idea here is there's this pathway that involves insulin sensitivity and fat cells, leading to fat cell engorgement, obesity. And in fact, some of the behavioral manifestations we see, eating behaviors and obesity, may be related more to this hormonal problem than vice versa. And so really interesting. And another thing that's nested in here is that neurons have insulin receptors. We all know this because of work looking at, things like IGF and ALS and other neuromuscular diseases, but there's a literature on insulin resistance, which is of course the mechanism in type 2 diabetes in neurons. And so this is really interesting science. I'm not an endocrinologist, nor do I pretend to be one. So if you don't want to read that article, this is a great article in STAT. And I liked it because it not only summarized the science and history, but it reminded me of Birch, and that the quote on the lower right is from a 1865 textbook, and it made the point, and you can read it in the STAT article, but makes the point that if you're a researcher and you go into some question with excessive faith in your theories and a preconceived notion, then you're only going to see what you want to see. And the point here being that obesity researchers decided what they wanted to see, and that's all they said. And there's an interesting history that revolves around where this research was happening and intervening World War II. So Rick Barron will love this article, highly recommend it. But a great quote also is that to think about obesity as an overeating disorder is like thinking about alcoholism as an overdrinking disorder. And this has implications for how we think about clinical trials in neuropathy. I think first we need to begin to think about the science of obesity in designing our clinical trials. So, taking a caloric restriction approach may not be the answer. Taking an approach that intervenes, and this science, I would say, actually validates things like ketogenic diet. Maybe that's where we should be focusing our effort. Regardless, clinical trials should be mindful to include biomarkers that inform disease mechanism, and both, we've got skin biopsy data, but liquid biomarkers, and invest in biomarkers. And then lastly, think about shared mechanisms. And depending on mechanism of action, I actually think now we're in an era where we need to think about trials that don't just focus on diabetes or idiopathic or cryptogenic neuropathy, C-SPAN without diabetes. I think these are close enough related that we ought to be thinking about them as metabolic neuropathy, to use Eva Feldman's term, which brings me to the last piece, which is about the topiramate trial, which is exactly that kind of trial. And like most, at least of my successes, I stumbled into it. And we don't know if this trial is successful in terms of outcome, but it's unequivocally successful, and it's being performed because it's the first randomized trial of a disease-modifying agent at scale in C-SPAN. And I think you're all familiar with topiramate. It's FDA approved for epilepsy and migraine. Most of you are familiar with the fact that it's approved for weight loss, and that turns out to be the most common side effect in taking topiramate in clinical trials. It's an interesting drug. It improves insulin sensitivity. It probably has central mechanisms in terms of weight, and it's also a ion channel mediator and a permissive voltage-gated sodium channel antagonist. So multiple different potential mechanisms. This is a meta-analysis showing that there's consistent weight loss across multiple studies, and the weight loss is not dose dependent. So you don't have to give people 400 milligrams sorry, I'm looking at the chat function here, 400 milligrams of topiramate to get the weight loss effect. And so those of you who've been around for a few years will also remember that this has been tried in diabetic neuropathy, and probably the best designed study was the CAPS 141 study that I won't get into details, but it was a positive study in terms of improvement in neuropathic pain. And there was definitely weight loss. This is the control group, and topiramate, the open label extension, showed catch up in the placebo group. There were two other large studies that had some methodologic issues that were negative, and J&J, which was developing topiramate for neuropathy, set the program aside. So we actually don't know. Herein is another interesting lesson, and this is to talk to your friends and colleagues. So the idea behind this trial came up in the back of a cab going to the FDA for a meeting where Bob Rappaport was going to school the neuropathy community about our failure to succeed in finding targets for neuropathy disease modification, symptomatic management. Some of you were probably at that meeting. And on the way, Bob Dworkin, who I mentioned earlier, said, I love your work and exercise. Have you thought about topiramate? Because it seems to work for neuropathic pain and it causes weight loss. Also in the car was Arthur Vinnick, endocrinologist, recently retired from Eastern Virginia, ironically. And he said, you know what, we've looked at this and it seems to work. And so he had published a small clinical trial of topiramate for 18 weeks. And there were significant metabolic benefits as well as improvement in neuropathic symptoms, and even some data suggesting improvement in epidermal nerve fiber density. And so the idea for this trial actually came from talking to friends. It wasn't my idea. And we were at a point where our funding was, we were turning over an R01 and some other grants, and I was casting a vote for ideas. And I thought, this is an interesting idea. Let's do it. And we were part of Neuronext, and the rest is what I'll show you here in a moment. Of course, topiramate also addresses another potential mechanism, which is gain of function sodium channel mutations. And so this is the original paper pointing out that patients who have idiopathic small fiber neuropathy may be at risk to have sodium channel mutations. Now, this is a controversial area. In the European literature, there have been multiple papers. This is another one showing that in patients with small fiber neuropathy, there seems to be an enrichment of mutations across multiple different voltage-gated sodium channels. And on the right, these seem to be functionally significant mutations. We don't see these. I've not found one. I don't know of any friends here in the U.S. who have. But we do know that in animal models of diabetic neuropathy, these channels are important and neuropathic pain and actually axonal degeneration. And so whether or not you believe in this sort of genetic hypothesis or not, these channels are relevant, and clearly pharmaceutical companies are looking for small molecule inhibitors of specific channels to try and modulate neuropathic pain. So there may be pleiotropic effects of topiramate. So the trial itself is important just by virtue of being done, and it has several other innovative aspects, and I'll talk about a couple of them here. The concept is pretty simple. We're looking at whether topiramate will impact neuropathy-specific quality of life and epidermal nerve fiber density. We have employed, I think, a pretty novel go, no-go decision, which basically is requiring ahead of time that there is efficacy in one of these markers and non-inferiority in the other. So if we see a symptomatic benefit and improvement in quality of life, but the epidermal nerve fiber density doesn't get worse, we'll move forward, and vice versa. So interesting statistical design. The other innovation, again, was luck. And that is as you can see with our enrollment, it was terrible in the beginning. And this is a really common disease. And so as you're designing trials, think carefully about your exclusion criteria. We didn't think carefully enough. And each one of these little bumps up down here, we kind of cleaned up the exclusion criteria. But actually, it was Tony Amato at a Next Executive Committee meeting. He said, "Why aren't you guys just having diabetic patients in this?" And something that never would have been passed through NIH for a whole host of reasons. But I said, I agree. I'd love to do that. I didn't think we could. And so with Tony Amato's great idea, right around in here somewhere, we said, let's include patients with well-controlled diabetes, and we filled the trial. So we actually ended up with the trial that is what we would have wanted at the beginning and what I would have wanted now by pure luck, which is something you make of it. And the luck came, and I've got one more slide just to talk a little bit about Birch, comes from the people you hang around with. And so this was a trial that came from people far smarter than me. I won't speak to Rob, but Rob's smarter than I am. But came up with an idea, and it succeeded by working in a group and having other people point out fairly obvious things that we had gotten wrong. And I think this trial is a great example of how we need to be thinking about obesity and other metabolic risks in neuropathy and their implications far beyond idiopathic neuropathy. Happy to talk more about chemotherapy-induced neuropathy. And these may even have implications in terms of thinking through regenerative capacity and inflammatory neuropathies with secondary axonal injury. So with that, I have to, and this is where I get really nervous because I'm going to say some things about Birch, okay? And so the first thing, I've learned a tremendous amount from Birch over the years, and still can't believe I'm giving the Griggs talk. I still feel like there's a joke at the end of this somewhere. And Birch doesn't remember when he first met me. I don't think. I was actually a resident, and he was one of the panelists at the AAN case conference. So that's a story for a different day. But over the years, I've interacted with Birch many times, as I know you all have. And I think maybe the first lesson on here is the extent to which truly transformational leaders and mentors impact the lives of people who they don't have ownership of. And actually, Jack Griffin is another person who played a similar role in my life, who's obviously no longer with us, who had no need to help me out. He had plenty of work to do at Hopkins, but he did, and Birch is in that same category. And I really think of these two individuals as, two of the most important people in my life. And so some of the things I've learned from Birch, there are many. I think one is Birch isn't always easy. He asks hard questions, which I'll get to in a moment, but he's always kind. And I think that's really important. Even if you are challenging someone or you disagree with them, be nice to them. That's really important. I think Birch is an optimist, and I've tried to learn to be optimistic, even if I'm not feeling optimistic. Maybe a little bit of Ted Lasso, although Ted's not Birch. He's no Birch Griggs. I think one of the things that I particularly appreciate about Birch is that he listens really carefully, and then he asks hard questions. And I think there's two points here, and that's the listening, but it's asking hard questions. And so I didn't put it here, but I've seen Birch in action through the Academy and the American Brain Foundation. And there's a courage about him in asking hard questions, and you see it in his mentorship, and certainly in my conversations with him. And he'll often ask the hard question in a very deceptively nice way. And so that's a really great skill and something I appreciate. Perhaps the most important advice I've received when I became chair, Birch told me this: keep your door open, your mouth shut, and laugh a lot. I do two of these really well. I have a real problem with keeping my mouth shut, so I need to work on that. And so Birch can give me advice on that. And something I've been thinking about lastly is as we've been struggling at the American Academy of Neurology and our own department, thinking about what it means to be a general neurologist, is that there's a specialist in every generalist and a generalist in every specialist. I hope Birch will be proud that I figured out hypnic headache. It took my fellow to help me out with that, by the way. But I'm treating headache in the neuromuscular clinic, which I'm pretty excited about. So Birch, I owe you an incredible debt of gratitude, as do everyone else here. And I hope I did you proud in the talk. There are a few comments in the chat. So I think one is 100 milligrams typically doesn't affect cognition. We actually have seen that as well. There was what we've learned is that if people are going to have adverse events from either their placebo or their topiramate, it happens very soon after you start the drug. There is a fairly high percentage of mild neurocognitive effects, but they're not durable. They get better when you stop. And so at 100 milligrams, it's not a major problem. And Deb Galinas asks about, I thought you had another one, Deb, about those unusual obese and very active patients. And I think this goes to the point about it's not energy expenditure; it's a hormonal problem. And so, Deb, I would, if you're into the obesity literature, read the journal from the American Journal of Clinical Nutrition. But the STAT article is where you should go. And so I'm going to stop. And just one other debt of gratitude to the team I work with. So Rob Singleton is the brains behind the operation, standing to my left, on your right. Eva Feldman in the middle. And this is really the work of all these people, Brian Callahan, who I mentioned a couple of times, on the right. And I think I've got slides from Radhika, Amanda, and James as well in there. So I'm going to stop. Thank you for listening to me. I can't see you, so I hope you're still there and I haven't torpedoed the meeting. Happy to answer other questions if there's time.
Thank you, Gordon. You could probably put it on gallery and see people. There are a few questions. Dr. Griggs, you raised your hand up. So did you want to say something initially? Can we unmute that?
Gordon, thank you for your wonderfully complimentary comments about me. I would have to say that for each of the things you attributed to me, I attributed them to somebody else. So I've learned from the people who mentored me all the things you mentioned. But your talk was wonderful, but it has to leave me wondering about what neurologists who are interested in treatment should be doing. Because I think it was Osler that said one of the principal differences between animals and humans is the desire of humans to take pills. And we find ourselves, I think, as neurologists interested in treating patients, looking for a pill that will improve the disease. When, as you pointed out, changes in lifestyle and the social determinants of health have such a major effect. And the recent papers in both New England Journal and JAMA are continuing to deplore the lack of a primary care infrastructure in American medicine. We're the only developed country that doesn't have enough primary care, and it's getting worse all the time. And as neurologists, we love having people go into neurology and love people who want to imitate us. But see, as we think about healthcare and treating diabetes and pain and other things, it's pretty clear that lifestyle would be very important, and having primary care physicians and nurse practitioners in sufficient supply to help address the problems might be something we should think about. So now you've just become chairman within the past 5 years, and so you're looking at reproducing yourself big time with young people. But what do you think? Should we really be doing that?
Yeah, I couldn't agree more. And interestingly, we tried to crack that nut in this space with a grant to the HEAL initiative, which proposed to leverage CTSA infrastructure and push this out into primary care settings. So develop a screening methodology, train people in primary care offices to recognize early neuropathy, and then develop essentially a curriculum for a lifestyle intervention. And we're even working on another idea, which is, can we leverage technology to the same purpose? Because, I think it's hard to get primary care doctors to take time to do this, right? They're under incredible pressure, financial pressure and time pressure. And so there may be other centralized health-based ways of doing this. And ultimately, I think this is sort of a health policy and care delivery model problem that hopefully, if we can get away from my former kind of boss and mentor in Utah, Vivian Leake, talks about our action-oriented healthcare economy. You get paid for doing things, you get paid for action, when we really ought to be paid for the value we bring. I think if we can start to move into more of a value-based world, that would help. I do think that there are pills on the horizon. I mean, I'm hopeful that topiramate will work, but something I didn't talk about are other things that are in the pipeline. There are other small molecules and others approaches in the therapeutic pipeline for diabetic neuropathy. I'm really excited about the SARM1 story. So inhibitors of programmed axonal degeneration. So I agree with you about the pills, and I'm hopeful that we can come up with both a better systems approach to health, which is what you're talking about, as well as innovative small molecule therapies that target relevant pathways for neuropathy.
Great.
By the way, Jim Albers, one of my other mentors, told me once that everything you say is an amalgam of the things that people say to you. And he said the same thing you said, that I hear specific people. And I think about that all the time, Birch, because I go around quoting Jim Albers all the time. So
there were a few questions, but we're really out of time. So I know Debbie Gelinas at Argenex, Sarah Jones had questions, but I think we're going to move on. Before we do, though, you're going to get this in the mail, Dr. Smith. We have this wonderful Dr. Gordon Smith, the Robert C. Griggs, MD, annual MSG lecture, Muscle Study Group, October 1, 2021. So this will be in the mail to you soon. So thank you very much. That was a great talk. I have a lot of questions and other people do too, but I think the advantage of the chat is that you can either chat to Dr. Smith directly, or you can do a group chat and hopefully he'll respond. There were a lot of questions about side effects of topiramate. What's the highest dose you can get to without cognitive changes? Zonogram, is it just as good? Things like that. But I think we just need to move on to the next talk.
It sounds good. I look forward to bourbon and cigars soon in person.
Yes. All right. Thank you so much. All right. So now I'm going to turn the program over to Senda Ajru Dries in Northwestern, who's part of our planning committee, and she is going to introduce the next part of the program.
Hello, everybody. We're going to change gear and move to muscle. Dr. Hanna and his group are going to present about the inclusion body myositis International Genetics Consortium study update. And Dr. Henry Holden will be presenting on behalf of the group. Dr. Holden, please take it.
Okay, so thank you very much for the kind introduction. So Mike's on in his office, you can see him there, and me and Alla are here. So I will hopefully share my slides with you. Here we go. Okay, so if you could nod if you see those, all right? Can you see them? Yeah. How about that? Perfect. So,
It's just the top. It's just the UCL part. That's okay.
Oh, that's okay. Yeah, it's okay. You're not missing anything by cropping off UCL. This is all Institute of Neurology. Different building, but anyway. So thank you very much. And we're going to have a little bit of a double act in terms of I'll do an introduction, and then Alla, who's the one who's been working on crunching the data, will give her presentation of the GWAS so far and where she's up to. So this is an update for everybody who's kindly sent samples and kindly worked with us over the last couple of years. So we're very grateful to you, and we want to show you what we've been doing. And that's this introduction here. So this is kind of my standard introduction slide. I don't really have to tell you this, and I don't have to tell you how important IBM is and how it's not an uncommon disorder. You know the clinical features, but it's often quite a tricky disorder to diagnose. And it's rather an interesting disorder of a combination of inflammatory as well as degenerative features. So it's difficult but interesting, and I think the genetics holds a lot of promise, and that's particularly why we're interested in it. I mentioned the inflammatory and degenerative pathways, and this maybe gives us some clues as to what genes to look for. You know, for example, the immune-related genes, HLA, but you wouldn't also be surprised if you saw certain risk factors in TDP, VCP, tau as well. So we wanted to use kind of a two-edged approach, both to look at targets in terms of these genes, such as VCP, which we did originally. This is a couple of years ago now. And it's not surprising to notice that some IBM patients do have VCP and there's P62 mutations. But when you look back at these patients, they're not usually classical IBM. They're usually patients that actually do have a cognitive component as well. But of course, we did this in the first instance. And we also, with many of you here on the call, we also looked at the risk genes. So we looked at Mendelian, we looked at risk, we looked at ApoE, we looked at TOM40, and we found there is some stratification, but it's not the answer. It's not the genetic association that we really wanted. So we also looked at HLA this was with the Manchester group, and pretty small number of IBM cases. And they found a small association with HLA, but the numbers were not powerful enough to really give the full story about independent risk. So we, probably about 4 or 5 years ago, we planned to do a combination of exome, genome-wide. This is so the exome sequencing global screening array to look at genome-wide study SNPs, so rare, common, and then sequencing of muscle IBM cases to see if we can pair this with the genome-wide data to strengthen our loci that we pick up. And looking, obviously, at inflammatory, looking at perhaps seeing if there's any overlap with other genome-wide association studies in inflammatory myopathy, in Alzheimer's, in FTD. You wouldn't be surprised if you saw an overlap between perhaps some of the inflammatory myopathies or with Alzheimer's or FTD in terms of their risk loci. They may be slightly different, but you wouldn't be surprised to see that. And so initially we did an exome study that allowed us to look at the candidates, but only allowed us to do an underpowered GWAS looking at some of the rare variants. And this picked up 2 loci. The one on chromosome 6 is HLA, and the one on chromosome 1 is a group of inflammatory genes. And I'll just let Ala just give you a little bit of a summary on those genes, because she's read about them and she can give you a nutshell on these, and then she's going to talk about her GWAS.
Hi everyone. So in previous slides, we have done the exome association analysis on larger IBM exome data, and we found the 2 interesting loci on chromosome 6 and 1. For chromosome 6, these have been mapped to 5 genes belong to family called
Chromosome 1.
Sorry,
Chromosome 1.
Chromosome 1. Yeah. Chromosome 1, and these have been mapped to a family called guanylate binding proteins. And this family is involved in pathway responsible for cytokines signaling immune system and also an innate immune system. These genes haven't been reported before with muscles or IBM, but it's emerging target in inflammation and also cancer, and will be very interesting to look at these few genes in our larger IBM GWAS.
So the reason to mention these genes is that anybody working on these pathways or anybody interested in delving further in the functionality, these are, I'm quite keen to share the variants as we find them so that you can do that. And that's, that's an important thing.
Yeah, especially this.
And then these are the GWAS numbers.
Yeah. We would like actually to thank centers who genotyped more than 1,000 IBM and also more than 2,000 controls. We have selected a number of more than 158K as shared by allelic SNPs between cases and controls to use it for GWAS analysis. we also would like to thank every collaborator and every centers who send us IBM samples to achieve this important goal in IBM project.
So that's the most important slide, I think, that the collaboration and the sharing of samples, because without that, then you know, we would have got nowhere. And the reason I'm talking a bit is I can't seem to shift this slide to the next one. Oh, we go. Here we go. Is that?
Yeah, this is the slide. We started to work on our IBM GWAS data. We start to clean up our data to remove any low quality samples or variants. These two figures show the distribution of genotype call rate per sample and per variant. Anything less than 98%, we removed it from the study. I think there is an issue with shifting the slides.
Don't worry. So basically, this slide says that the DNA was good, the genotyping was good, and we were pleased with the call rate. Now we'll see if we can get the next slide. No, we can't. Let me. There we go.
The other thing is,
Maybe, don't keep pressing it, otherwise we're going to get loads. There we go.
We can go to.
Why don't we go to this one?
Yeah.
So why don't I? Can you see that still, everybody? Yeah. Okay. I'm hoping that does it now. Yeah, the slides is very small. There's no videos or anything. It's just a bit slow.
Can you still see the figures from the slides?
Can you see the figures?
Yeah.
Yes, we can.
Yeah. Why don't we just stick with this and crack on?
Yeah.
Because otherwise, you know.
Yeah, this will take long to upload.
So if you give a summary, quick one-liner on each one, and don't press any more buttons, Ella.
Yeah.
And then
So this slide is just to show that the genotyping information regarding gender information is matched with our recorded 6, so we don't have any issue. And also, it's important to have independent GWAS samples. There is no duplication or relatedness. Also, we checked for heterozygosity genotyping to check if sample is contamination or there is inbreeding. Yes.
The next slide shows you.
The next slide shows the population stratification to make sure our samples are European ancestry. So we merged them with the HubMap data, and they are clustered with the European HubMap population. Any sample deviate from this cluster point, we removed it from the study because it's indicated mixing ancestry between European and other population. We also tested for population stratification within IBM control. Within IBM and control, a few samples was identified as outlier samples. Then we needed to remove from the study. We have done now the control on the data, on the IBM data, and we are going to use the haplotype reference consortium to for imputation, and that's why we will check the data set for accuracy relative to expected haplotype reference consortium before the imputation. We expect to finish the imputation and post-imputation QC in October, and the whole GWAS analysis by early November. Hopefully, we will have nice data and everyone will be happy with the GWAS new findings.
So that's the plan, is to combine the GWAS with the exome and then use the RNA sequencing to see if we see aberrant expression over the exome or the GWAS associated loci, to try and effectively haplotype it and associate it with aberrant expression if possible. But if we see just a GWAS loci, I think that will be important to then share with everybody to try and, well, give early data and also to see what pathways we get. So that's our plan over the next 3 or 4 months. I think it's an exciting time of the GWAS because Previously, we'd be just collecting samples and analyzing data. But I think now is where the money will come in terms of our findings. So thank you very much for listening.
Thank you for listening.
Any questions, we are happy to take.
We do have 3 minutes for questions.
One from Mike there.
Yeah, I just wanted to reiterate that it's only because of the MSG and all the colleagues listening and on that list and others that it's been possible to accumulate such a large number of IBM patients. And as we all know, for GWAS studies, the power is determined by the numbers. So this is an incredible resource that is a shared resource with all of the MSG community. And we want to continue to build it, actually, now that we've got this far. So it's really just a thank you to Birch originally for suggesting this, actually, and for Rick and others on the committee for allowing this to be a somewhat unusual MSG study, in that it's not a trial, but we hope it will continue to bear fruit. Thank you.
Yeah, thank you as well. I appreciate that, definitely.
Can I ask a quick question? Maybe I missed it. The controls are normal controls, correct?
Yes, we didn't want to spend money on controls, so we took very dense Wellcome Trust European controls to allow us to get them for free. So that was a benefit to us because we wanted to do it as cost effectively as possible. And I had a question from Tom about, Tom's interested in the GPP genes.
Mm-hmm.
What do you think, Alan? How do you think the GPP genes affect IBM in terms of the function?
GBP is involved in immune system and cytokines signaling pathway, and its emerging target in inflammation. Since IBM has also inflammatory pathway, this might be contribute in inflammatory pathway of IBM.
So if we saw those genes overexpressed in the RNA sequencing from the muscle biopsies, then that would be very exciting. And I think that would be important to share early with people like Tom, because we want your insights into this, into what they're doing. Because a lot of GWASs, they produce loci, associated regions, but they don't actually infer on what the function could be. So that's, that would be exciting, hopefully.
We have a chance now also to look at this gene again in our largest IBM cohort for GWAS to replicate this association. And that would be good.
A couple more questions. Do worry if patients have sporadic IBA. Several subjects have no mutations in genes. Yeah, I mean, when there is a worry about having single mutations, and you'd like to think the exome would pick out the rare variants in known genes, and then we could exclude them. We've actually genotyped everything to allow us to actually pick which data to include and to take them out or not to include them. I suppose that's the beauty of the GWAS data, and also the other beauty of the GWAS data, we can share it with people as well, and then we can build on it as years go on. We have also seen Alzheimer's surgery. Yeah.
We do probably have to leave these questions for later, as we need to move to the next talk.
Okay. Well, thank you very much.
Thank you very much, Dr. Holden and Dr. Hanna's group. Now we have Professor Neil McHugh, who's going to talk to us about antibodies and myositis.
Thank you. Let me share my screen. Thank you for everyone, and thank you for the invitation to participate in this meeting and for tuning in to this talk on autoantibodies and myositis. So while my focus is on myositis, you have to forgive me as a rheumatologist for pointing to these other conditions listed here, really to make the point that whilst we're tied to certain diagnostic and classification criteria, it's quite remarkable that each of these conditions is characterized by a highly tuned autoantibody response to a very restricted repertoire of intracellular molecules, as you can see here, for reasons that we still don't really fully understand. And as well, the autoantibody profile not only identifies specific clinical phenotypes within these conditions, but this autoantibody repertoire may also prove a useful device for identifying pathogenic pathways or indeed endotypes. And I'm going to really concentrate on that in terms of myositis. I don't have an arrow to move this far. I'll just see whether okay, I can do it with my cursor. So excuse me. So here is that autoimmune response that I showed previously. And the autoantigen targets are designated in these circles, as shown in this bubble diagram. And each autoantigen clusters not only with individual conditions, but with patterns of disease within the parent condition. And this is shown in this upper triangle here for myositis. Now, from a historical perspective, it's worth noting that you can go back to more than 40 years from when the first truly myositis-specific autoantibody was discovered, MI2, then Jo1. They were first reported that time ago. And it's only relatively recently, or at least in the last 10 or 15 years, that new specificities have been discovered such that nowadays one would expect to find a myositis autoantibody in the majority of new cases of myositis, although certainly not in all. Now, here is a list of the main so-called myositis-specific autoantibodies from one of our group's recent reviews. And note that without exception, the autoantigens play key roles in either gene transcription, protein synthesis, protein translocation. NXP2, for instance, is a tumor suppressor gene. MDA5 plays an important role in innate mechanisms dealing with viral infection. And all these processes may be upregulated or disturbed by factors such as viral infection, ultraviolet light, cancer, and in the case of HMGCR, indeed ingestion of statins, for instance. Apologies for another one of these bubble diagrams, but this is from an older review, and it still quite nicely summarizes in a little more detail how myositis autoantibodies do associate with distinct patterns of disease. For instance, lung disease or interstitial lung disease is a key component of the antisynthetase syndrome, and indeed may be the only manifestation without any apparent muscle involvement at all. Anti-MDA5, a more recently discovered antibody, is associated with rapidly progressive lung disease, more so in Asian populations. Whereas skin disease is more prominent with MI2, one of the original autoantibodies, and also an antibody system that we reported ourselves, anti-SAE, or small ubiquitin modifier activating enzyme. In our own experience, and that's been substantiated by more recent findings as well, patients with anti-SAE include those who present with quite florid skin disease and little, if any, muscle disease. In other words, clinically amyopathic DM. But many of these patients do go on to develop quite significant muscle inflammation. And one important observation that many groups have made, and indeed this comes from a large European study that we conducted, is that, and it is possible to generate these type of diagrams, is that myositis-specific autoantibodies very rarely coexist. This is that study where we've measured the autoantibodies by a technique called immunoprecipitation. Now, this almost mutual exclusivity of MSA again underlines how useful they are, not only as diagnostic markers, but also as tools to dissect mechanisms and genetic subsets of disease that I'll touch on later. Other points to note from this study is the association with SRP with carditis, though not all studies have shown, but we did show this here. And as well as that, a relatively large group of patients with as yet no definable myositis autoantibody detected. But obviously there may be some out there ready to be detected. So I'll briefly touch on some of these syndromes defined by autoantibodies in a little more detail. And one of the first myositis autoantibodies to be described, as I mentioned, was anti-Jo1. That's directed to histidyl tRNA synthetase, and subsequently other autoantibodies to tRNA synthetases were also discovered, although in relatively fewer patients. Now, it's important to recognize that there's also a degree of heterogeneity within the syndrome, as illustrated here. Whereas the non-Jo1 antibodies are more likely to be associated with lung disease on its own, whereas anti-Jo1 in fact picks up a good percentage of patients with arthritis. I should also add that the technique that we use quite frequently of radioimmunoprecipitation of proteins from radio-labeled cell lines is a very useful technique for detecting an array of the myositis specific antibodies, but it's not widely available. The other important autoantibody that has very much come onto the radar in recent times is anti-MDA5. Which, as I think I mentioned, is much more common in the Asian population than in Caucasians, and importantly is associated with rapidly progressive ILD that can actually be fatal. So it's important to recognize this group. One observation is that these patients do tend to get typical sort of ulceration, both oral ulceration on their hands, as seen here, palmar papules. A similar condition also is seen in children that I've got a slide on. Now, for a description of immune-mediated necrotizing myopathy, I think I can't do any better than refer to this excellent review here from Yves Allenbach and colleagues. So points to note are the strong association of anti-SRP and anti-MGR and anti-HMGCR, which is seen in about 80% of cases. It's associated with severe muscle weakness and high CK levels. And there does seem to be an additional risk of this with anti-SRP, with myocarditis and with ILD. It seems that the patients who are seronegative might actually have a slightly increased risk of cancer. The other feature, as shown nicely in this review, is characteristically sarcolemmal complement deposition, a frequent feature. And also, I've mentioned here some of the data suggesting that these antibodies may in fact have a direct pathogenic role by targeting ectopic presentation of antigens on regenerating myocytes and myotubules. You do see this syndrome in children. A few groups have reported this, but this is our series from a large UK collection of juvenile myositis. And again, the 4 cases here, the 4 children had severe myositis, all requiring quite aggressive treatment, high CK levels. They also had biopsies showing necrosis, patchy inflammatory infiltration, and again, MAC deposition on sarcolemmal membranes. Just a summary slide. We've looked at a large cohort of UK patients with JDM. And it's worth noting that these relatively newer MSAs make up more than half of the total number of cases. Similar to adults, they're mutually exclusive, and they also associate with certain patterns of disease, as noted here, in XP2, for instance, with sometimes with calcinosis. The only differentiating factor is in children, anti-TIF1 gamma, unlike adults, doesn't seem to be associated with the presence of cancer. And I'll turn to cancer because, of course, you'll be aware of the association of cancer with myositis, more especially with dermatomyositis, and the common forms of cancer are listed here. This PET scan shown here comes from a patient of ours who presented several years ago now with a fairly ill-defined systemic illness, myalgia, interestingly a normal CK, but the PET scan showed recurrence of a renal carcinoma affecting bowel and a lymph node. In fact, this was resected, and he's done well. But this patient did have anti-TIF1 gamma, and to illustrate the association with cancer. And again, the association of TIF1 gamma with cancer is well illustrated in this recent NICE meta-analysis that showed the association, a relative risk of 4 to 5 within an IIM population. Rohit will be pleased to see that slide as he was a leader on that study. So, of course, it is intriguing that TIF1 gamma and indeed many other myositis autoantigens, in fact, are upregulated on regenerating muscle fibers, and indeed also in tumor cells from cancer-associated myositis individuals. So one could conceive that in certain situations, given a combination of the appropriate genetic and environmental factors, autoantibodies in myositis may arise from an initial anti-tumor response to mutated peptides in cancer tissue that somehow becomes misdirected to native TIF1 gamma or to other host antigens. It may also be possible that even in those patients who have myositis but don't have cancer, or indeed other autoimmune, or indeed in other autoimmune conditions, that the development of myositis or those autoimmune conditions is the unfortunate consequence, or the immunological price, if you like, to pay for successful tumor eradication. Now, I mentioned on the previous slide that many myositis autoantigens are upregulated on regenerating muscle cells, and this study is interesting in that this finding is also borne out if you look at RNA levels. They used RNA sequencing to determine RNA levels on several myositis, on muscle tissue, and looked at for several myositis autoantigens from patients with different myositis profiles. The interest here is that for the most part, while the autoantigen, the RNA levels are overexpressed, the overexpression does not correlate that well with the autoantibody from that patient, implying that there must be other factors other than simple autoantigen upregulation that determines the autoantibody specificity. And one of those factors is very likely to be genetically determined. And evidence from this comes from this European study of 2,500 patients with idiopathic inflammatory myositis. They had high resolution HLA alleles and sequences imputed from existing genotype data, and they were tested for 12 different autoantibody groups. Now, just note, no surprising that Jo1 or anti-Jo1 associated with an ancestral haplotype, a strong association with DR3 that has been found before. Interestingly, TIF1 gamma with a DQB1 locus, PMSCL also with DQB1, also associated with DR3, MI2 with DR7, anti-CN1A, because we did include patients with IBM. There did seem to be an association with DR3 and anti-HMGCR with DR11. Now, intriguingly, at the DQB1 locus, and I think this is quite interesting, there does seem to be a difference in association between adults and juvenile onset disease with anti-TIF1 gamma, and that adults have O202 increase, whereas children have O201 increase. And perhaps that goes some way to explaining the association of malignancy in adults, but not with children. But there may obviously be other reasons as well. But it's intriguing that, and this needs to be borne out with further studies, of course.
Professor McHugh, we have 2 minutes left.
Okay, thank you. Yeah. So I just last couple of slides, and I'll touch on autoantibody problems in terms of autoantibody measurement, and point out that immunofluorescence is a very useful screening technique, but usually needs to be confirmed with other assays, with myositis usually by line blot or ELISA, but if you've got access to it, immunoprecipitation. But there are problems. This is a screening immunofluorescence. Sometimes that can pick up the antibody like anticentromere. But as I've mentioned, beware that your patients with anti-synthetase antibodies may be reported ANA on screen because they have a cytoplasmic pattern, as shown here, that may not be reported. So that's one thing just to check on. We did a large survey of the IMAX community, about 111 different centers worldwide, to see what assays were commonly used. Note that line blot and ELISA were the most common assays used. I think this is almost my final slide, but we have recently looked at the reliability of immunoassays to detect MSAs, comparing immunoprecipitation with line blot. And I'll come to the main conclusions here, that line blot doesn't pick up TIF1 gamma in almost half of cases. So there's a problem with the line blot there. Otherwise, it does quite well. But the other problems, it over picks up anti-Q, over picks up anti-PMSCL, and it doesn't pick up anti-OJ at all. So there are some issues there. So my conclusions, and I might even be on time, myositis autoantibodies have become important tools for diagnosis, patient management, and they do identify distinct patterns of disease. I hope I've given you a little bit of a glimpse that the myositis autoantigens do provide insight into mechanisms. I mean, I've touched on the problems we have with reliability of some of the commercial assays that are being used, and I'll finish there. Thank you.
Thank you very much for making this very complicated topic a little bit simpler. There is one question that came in, I think, and we only have the time for one. There is a question about doing repeated malignancy screen in patient with TIF1 gamma if the initial screen is negative.
Yes, I think actually that's something which is being worked on by the IMAX group, and with guidelines coming up for cancer screening. I think most would say that within the first 3 years that screening should be repeated because the cancer may not arise or may not be immediately obvious. So I think it's worth screening initially, but then repeating the screen 12 monthly for 3 years. But guidelines need to be produced for that scenario.
Very good. Thank you very much. Thank you very much, Professor McHugh. We're moving to Dr. Rohit Agrawal, who's going to talk to us about interventional studies in myositis.
Well, first of all, I want to thank to Muscle Study Group for inviting me to present this talk. I'm going to present on clinical trial updates in myositis, and it's quite a difficult task to present in 20 minutes. 5 years ago, I would have done it in 5 minutes because there weren't that many trials, but now it's becoming more and more difficult because we have a lot of clinical trials going on in myositis. With that, here are my disclosures. And I'll jump right onto a couple of introductory slides. As you already know, Dr. McHugh already presented excellent talk on myositis overview and autoantibodies. So I won't bore you again. But, a heterogeneous systemic autoimmune disease, myositis is a heterogeneous systemic autoimmune disease, the primary target of muscle, skin, and a lot of people would now say muscle, skin, or lungs because those are the three most common organ involved. Traditionally, we have 6 clinical subsets: adult myositis, adult dermatomyositis, juvenile myositis, which is mostly juvenile dermatomyositis, cancer-associated myositis, which is also mostly cancer-associated dermatomyositis, and then overlap myositis and inclusion body myositis. However, I want to point to 2 new clinical syndromes that are now should be recognized as distinct clinical syndrome, which are necrotizing myopathy and clinically amyopathic dermatomyositis. In addition to antisynthetase syndrome, which is more of a seroclinical subset rather than pure clinical subset. Here are, before we jump into the update on clinical trial, this will be my slide before I review any clinical trials on the treatments of myositis. We start with steroid. First line often is methotrexate or azathioprine. Second line could be combination therapy or mycophenolate or tacrolimus. And a third line therapy would include rituximab especially for patients with ILD and antisynthetase syndrome, and also cyclophosphamide. In US, Acthar gel is also approved for myositis. And then we go to experimental agents such as abatacept, tofacitinib, and tocilizumab. And then on the side, you also see that IVIG kind of goes from first, second to third line, because up until now, we've been using IVIG whenever we want to use it, whenever we need help. And I have to say that every time I use it, it comes to a significant help, whether I use it as first line or during second line or third line. It has a significant benefit. And then last but not the least, these figures on the side in the white and black are trying to show the importance of exercise to start early and to go all the way until the myositis is completely better. So the future of myositis, this is a slide I prepared about 2 years ago. And since then, I would say 4 or 5 more myositis pipeline drug has been added. And these pipeline drugs are mostly in phase 2 stage or trying to get into phase 2 stage. But now we have 5 drugs completed or underway phase 3 clinical trial. And I would like to highlight one of them, which has completed phase 3 clinical trial recently and got FDA and EMA approval for dermatomyositis, which is IVIG. So I'll start there. So IVIG Octagam is the only FDA and EMA approved therapy for dermatomyositis, which is based on phase 3 clinical trial results. So in this clinical trial, well, first, before this clinical trial, I want to give you a little bit background on IVIG. As you've obviously, a lot of neurologists in this group use IVIG a lot more than I have used, but the evidence of IVIG in myositis comes from Delakas et al. Study of 15 refractory dermatomyositis patients. This was a randomized, double-blind, placebo-controlled crossover design in which half the patient got IVIG early for 3 months, and then they were put on placebo, and then half the patient got placebo early and then was switched on to IVIG. Overall results were significant in terms of more than 60% patient improved with IVIG, and none of the patient improved during being on placebo. But then that study was then subsequently followed several decades later with 2012, another randomized controlled trial of only 16 patients with dermatomyositis and polymyositis, which actually showed there was no difference in MMT or CK in patients with IVIG versus placebo. Although there are a lot of issues with that study because only one dose of IVIG was given, the period was very short, and so on and so forth. But nevertheless, that was a negative study. That led to the phase 3 study. This is the ProDerm study that is recently completed called Efficacy and Safety of IVIG, which is Octagam 10% in patients with active dermatomyositis. And this has been presented at ACR 2020. So first, the study design, this was a prospective parallel group, double-blind, randomized placebo-controlled trial. So we screened the patient, 95 patients with active dermatomyositis, and these patients were randomized 1:1 to IVIG or placebo. These patients receive IVIG 2 grams per kilogram every 4 weeks for 16 weeks or placebo IV fluids. At 16 weeks, they would then move on to an open label phase where everybody got 2 grams per kilogram every 4 weeks till the week 40, except if the patients were doing well by week 28, they could reduce the dose to 1 gram per kilogram in the extension phase. What were the inclusion criteria? The inclusion criteria was adult dermatomyositis as per Bowen and Peter classification criteria. They had to have active disease. Each patient underwent independent adjudication to confirm active disease. These were refractory patients, which means they have either failed or intolerant to standard immune suppression. And typically, patient had failed either one steroid plus another immune suppressive drug, and they had to be weak. Their MMT score, 8 score had to be less than 142 by 150 with at least 2 other myositis core set measures abnormal, which include patient global disease activity, physician global disease activity, extramuscular global disease activity, muscle enzyme, and health assessment questionnaire. The primary outcome was the patient's proportion of responders at week 16, which was the double-blind placebo-controlled phase. And then the response was designed as more than 20 points on total improvement score, or TIS, which is the new 2016 ACR-EULAR myositis response criteria, which is the criteria now being used for most myositis clinical trial. And this total improvement score, or TIS, is based on 6 measures. So it's a combination of 6 measures, which include manual muscle testing, physician global, patient global, health assessment questionnaire, muscle enzyme, and extramuscular disease activity. So overall, we screened 126 patients. We randomized and treated 47 patients with IVIG and 48 patients to placebo. In the first period, which is 16 weeks, 95% patients completed the trial. In the open label, more than 70% patients completed the trial. What's important is most patients met definite criteria in Bowen and Peter, more than 70%, and total of 95 patients were included, with 53 as a median age, 75% female, and 92% Caucasians. So what were the results? So the primary outcome was significant, highly significant, because 78.7% patients improved with IVIG by week 16, and only 43% patient improved to placebo, with high delta of 35% and very strong p-value. But this was a minimal improvement. That means there was a minimum threshold the patient could achieve, which is technically very easy to achieve, and that's why you see very high placebo rates. But then we go to the moderate or major thresholds, which are much harder to achieve in this total improvement score. We see that 68% improved in this moderate criteria, and only 22% improve with placebo, with very high delta and p-value. And then if you look at the major improvement, which is very, very difficult to have patients improve within 16 weeks to get a major improvement, was about 32%, was 4 times as compared to the placebo patients. And this is a nice graph where you have on the y-axis mean TIS, and x-axis you have time or weeks. And you see the blue lines and dot represents IVIG, and gray line and dots represent placebo. So you see how these 2 lines separate early on, and by week 16, they're very different from each other, with a mean score of 21 versus 48. But when the placebo gets the treatment of IVIG and open label, it also shoots up and gets much better, and almost at the same slope as initially IVIG patient, and subsequently they plateaus but continue to get improved by the week 40. What about that's the total improvement score, which means basically it's a mixture of all different outcome measures. But what about individual outcome measures? What individual outcome measures improved? And almost all measures include MMT, CDASI, which is a skin disease activity of dermatomyositis, and all other measures improved except muscle enzyme. And we know for dermatomyositis, CK or muscle enzymes are a very poor biomarker. So it's not a surprise that they did not significantly improve, but everything else improved. What about the side effects? The most common side effects were infusion related. Most of them were mild, and most commonly, you already know, headache, pyrexia, nausea. So it's not a surprise to you. What was a little bit of a surprise to me, if you look at the serious adverse event, it was very similar in IVIG versus placebo group. But when we look deeper, we look at the serious adverse event, they were mostly thromboembolic events, PE, 2 CVAs, 1 DVT. This is within first 16 weeks. So we realized that obviously we know IVIG can cause thrombosis, but we had not experienced that much. And we know dermatomyositis caused thrombosis. So I think this 1+1 led to more thrombosis than we expected. So what happened is during the trial, we talked to FDA and we decreased the infusion rate, the maximum infusion rate. And when we decrease the maximum infusion rate, the thromboembolic events goes from 1.5 per 100 patient months to only 0.5 per 100 patients months. All right, switching gears, because I know my time is very short here. So I'm going to switch gear to another phase 3 clinical trial on a drug called linabecim. This is a synthetic oral small endocannabinoid mimetic drug. Basically, it's a selective agonist of CB2 receptor, cannabinoid receptor 2. What happens is when the drug interacts with this CB2 receptor, which is present in immune cells, muscle cells, endothelial cells, and fibroblasts, it induces various post-genetic activity, which ultimately leads to decrease in inflammation and fibrosis. Because of this, has been tried in scleroderma, because that's a fibrotic disease, and myositis because of the inflammation. And the phase 2 study of this was very positive. A phase 2 study on safety and efficacy was done by Dr. Worth et al., where they showed that CDASI, which is a skin disease activity, as an outcome measure in dermatomyositis. These patients all had very bad rashes, may or may not have muscle weakness, but had bad rashes. And they showed with these blue lines and boxes, you see the placebo, and then the, orange line and boxes, you see the placebo, and blue line and dots, you see the linabecim. And you see very early on, by week 16, they separate out in terms of CDASI or skin disease activity. And when the same patient gets enrolled into open label, they continue to improve all the way up to another 28 weeks. So that led to a phase 3 clinical trial by a company called Corbus, where they studied dermatomyositis patients. This was a randomized controlled trial. Initially, the study was designed to be 52 weeks, but then they cut it short to 28 weeks, and it was 2:1:2 design, 20 milligram versus 5 milligram versus placebo. And the criteria, the primary outcome criteria, was again the same TIS from ACR-ULR myositis response criteria. And they enrolled 175 patients. So unfortunately, this study did not meet the primary endpoint of total improvement score at week 28, unlike IVIG. At week 28, linabecim 20 milligram twice daily achieved the mean TIS of 28, which was similar to the control group of mean TIS of 27. If you remember, the mean TIS in 16 weeks in IVIG was 48. So very different from IVIG. And at week 52, these patients did show some trend of improvement. And if I remember the graph I showed you about CDASI, these patients improved early on, but then they continued to improve on long-term basis. So some patients were followed for week 52, and those patients seems to have a little bit better improvement as compared to control. But if you only look at the muscle weakness, or if you only look at the skin, then there are some significant trends there. The 20 milligram dose was better if you only look at the muscle weakness for muscle outcomes, and it was better if you only look at the skin involvement for skin outcome. Now, moving on to the third phase 3 clinical trial, abatacept. As you may or may not know, abatacept is basically inhibits the T cell co-stimulation. So normally T cell is activated when an antigen presenting cell presents an antigen on MSG molecule to the TCR, which is the T cell receptor, but then it needs a second stimulation, which is because of the CD8086 combining with CD28. This second signal leads to further activation of the T cell. But what does abatacept do is this blocks this second stimulation that then prevents the activation of T cells. So what happened with this drug is that the randomized controlled trial, a pilot phase 2 trial, was done by Dr. Ingrid Lundberg and group, where they gave abatacept injections every week for 3 months and versus placebo or no treatment for 3 months. And then the patients on placebo started getting treatment after 3 months. So half the patient got drug for 6 months and then didn't get anything for 3 months, and half the patient got nothing for 3 months and then got drug for 6 months. And on the graph that I'm showing you is total improvement score again, where you see the black line, which is the drug early, improves quickly within the first 3 months and then continue to improve a little bit by 6 months. But the placebo did not improve. The red line did not improve in first 6 months when they did not get the drug, but then they improved significantly when the second half, when they get the drug. So overall, 50% patient got better with abatacept in treatment early versus only 11% in delayed treatment. That led to a phase 3 clinical trial, which was another randomized control phase 3 clinical trial by BMS for 24 weeks. Here, the primary outcome was IMAX DOI, which is the same outcome measures used in rituximab. So the top line result of that phase 3 trial is that abatacept failed to meet the primary and key secondary endpoints in this, where 75 patients got abatacept, 73 patients got placebo, and it really just missed the p-value by 0.08. The real question is, since it's so close to the p-value, would the outcomes be different in patients with myositis autoantibodies? As we know, abatacept in lupus and RA works much better in patients with autoantibodies as compared to patients without antibodies. And also, could there be different subsets that are better? So could perhaps dermatomyositis versus necrotizing myopathy versus PM? And if you look at the subset, did any of those subset did better than the others? Moving on to JAK inhibitors, is becoming very popular drug amongst myositis colleagues here. Tofacitinib, it's a JAK inhibitor. It blocks multiple different cytokines, including interferon signal. And this was a pilot study. This wasn't a phase 2, but a small pilot study of 10 patients. It was open label, where they treated patients with refractory dermatomyositis. Now here, the problem was that mostly patients had skin disease, not so much of muscle disease. And they clearly showed improvement in the skin disease over the week 12, as shown on the slide. But the real question is, would it also work for muscle, which we don't know. And there's a phase 3 clinical trial that might be planned in subsequent futures. But want to also point about the use of tofacitinib in clinically amyopathic dermatomyositis, specifically in MDF5 patients, because this was an NEJM study where 18 patients got open label tofacitinib. So in these severe MDF5 positive patients, these patients have rapidly progressive ILD. And if you see the tofacitinib, 100% of these 18 patients survive. And if you compare historically, there's a high mortality associated with this rapidly progressive MDF5 positive ILD. So there is some signal for sure as well here in ILD world. Last but not the least, tocilizumab in myositis. This is a study again from our center where we did a simple randomized controlled trial. This was a phase 2 trial. We randomized patient 1:1. Total target was 40 patients. Half got drug, tocilizumab, which is an IL-6 inhibitor, and half got placebo for week 24. Unfortunately, this was also a negative study. As you can see, the placebo and tocilizumab mean TIS score were not that significant. And if you look at the over time, the graphs were overlapping between the placebo and treatment. So this is another study that failed. That brings me to my last or final slide, where how do I change? Now we have one phase 3 clinical trial, which is positive, which led to FDA and EMA approval for dermatomyositis. However, we have 2 other phase 3 trials this year failed. Very unfortunate for us, but at least we have a 33% success here in 3 phase 3 clinical trial reported this year. So how does it change my paradigm? I think I'm going to include more of IVIG for dermatomyositis as a first line, perhaps maybe also second line and third line. It was always an option, but it would be much easier for us to get approvals on IVIG in patients with dermatomyositis, which in past has been a problem. With that, I want to thank you for inviting me. And, here are some, I do some education on YouTube for myositis patients. And here are some other contact information. Thank you.
Thank you very much. Interesting, very interesting talk. We do have time for a few questions. Maybe I can quickly start about the rationale of using 2 gram versus 1 gram after the loading dose for the dermatomyositis study.
Yeah, so the rationale of 2 gram versus 1 gram is that traditionally all the studies, all the data, and we looked at 7 prospective studies, 2 randomized controlled trial, and majority of the drug use, of the dose used, was 2 gram per kilogram. That was the main reason. But also, when we ask clinically, most rheumatologists and many neurologists use 2 gram per kilogram dose. So we didn't want to risk it. We just wanted to go with the most effective drug. As when you do clinical trials, your first goal is to go with the most likely a drug dose that will get you a primary outcome. Once you have that outcome, then you can do dose response and other studies.
It is interesting to see that dose was actually well tolerated for the amount of time. So this is encouraging for us to kind of not be afraid and using high dose IVIG in certain patients who may not respond to the just 1 gram per kilo.
Sure.
I don't know if you mentioned it. Did you get into it all, the rituximab trial?
No, I did not, because, I had a lot to cover, and rituximab has been covered in past. But rituximab trial, if you remember, was another phase 3 clinical trial, which basically was a negative study, but there were very refractory patients in that trial, and 85% of those patients improved. So we do believe that rituximab works. And we did another post-hoc study on rituximab trial where we showed that the patient with anti-synthetase syndrome, especially do a lot better on rituximab than patients without autoantibodies.
Yeah, I was part of Dr. Otis's team when we designed that, and he was forced by the NIH to do that trial design. It's unfortunate. We should have just randomized patients and let them go for 6 months.
I agree.
And then we would be able to prove it, but they didn't let us, and here we are.
Dr. Mozaffar has his hand up.
Can we see you?
Can you guys hear me?
Yeah, we can hear you.
We can hear you.
Yes, I just wanted to make a comment about Rohit's comment about anti-synthetase syndrome, that it's purely a serological phenomena, but there's also a very distinct histopathology associated, which is different from dermatomyositis. So it's actually more than just a serological epiphenomena there, and they really truly are distinct from dermato and polymyositis from that sense. So I think there is a need to revisit that, and at least most new classification systems do include anti-synthetase as a separate entity. The second point I wanted to make was in the A-beta-CEP study, I've looked at some of this, the deeper analysis, and it does appear that there is a stronger signal in necrotizing autoimmune myopathy. So it's one of those situations where when we do myositis trial, we tend to lump all myositis into it, but there may be a stronger signal in some of the antibody-associated myositis, similar to what happened in rituximab.
Absolutely. Very, very well said, Yassine. That's absolutely right.
Very good. Thank you, Dr. Agrawal. We're going to move to the next talk.
Sure.
And we invite Professor Olivier Benvenisti to talk to us about the rapamycin study.
So I will present you the rapamycin study for IBM patients. So this study was published 1 year ago already in the Lancet Rheumatology with one comment, as you can see here. So why the rapamycin? To my view, my opinion, the physiopathogenesis of IBM is one autoimmune disorder with particular CD8 cells, cytotoxic T cells, T8 cells, that we call TEMRA cells, which are resistant to conventional immunosuppressive drugs. And we have shown with others that there is one accumulation of those cells in the peripheral blood of IBM patients compared to other myositis patients. I mean, dermato, immune-mediated necrotizing, and anti-synthetase. And on these markers, you can see that we have a ROC curve pretty good in terms of sensitivity and specificity for IBM. So these TEMRA cells are capable to synthesize a lot of type 2 interferon, and this interferon can have different effects on the mitochondrial function, bad effect, I would say, and also on the degradation of the proteins, particularly on the proteasome and on the autophagy. So the idea of the rapamycin was to counteract all these effects, notably on the TEMRA cells. Rapamycin is known, so yes, TEMRA cells, rapamycin is known to block the TEMRA cells, but also rapamycin can have one positive effect on the mitochondrial function and on the autophagy, re-increasing the autophagy. It has been shown, for instance, in Alzheimer model in mice, you know that there are some mimicry between Alzheimer disease in the brain and IBM in the muscles in terms of misfold protein accumulations. And it has been shown that rapamycin in those models of Alzheimer's disease can ameliorate the mice in terms of survival, but also of their ability to do some tasks and so on. So because of this anti-accumulative properties of the beta amyloid proteins and by the autophagy enhancement. So regarding the outcomes for the trial, we started not from nothing. We performed this and published this observational studies of natural history on IBM patients. And we perform over time without any treatments these muscle measures using these different devices, and also the 6-minute walking distance at 9 months and 4 years later on 16 different IBM patients. So first at day 0, we can observe that as expected, the weakness is more pronounced in the hand grip and the knee extension. And regarding the knee extension, we can observe after 9 months a decline, a significant decline compared to the other measures. Furthermore, we can, after 4 years of follow-up of the patients, you can see that we have a ceiling effect for the 6-minute walking distance compared to the knee extension strength, meaning that if you have less than 40% of the normal expected value of your strength in the quadriceps, then the 6-minute walking distance remains the same. Below 40%, then you have a clear decline. So that means that maybe for a clinical trial, if you include patients over 40% of the strength, then you cannot catch any improvement or decline using only the 6-minute walking distance. So that's the reason why we use this, the strength of the quadriceps as primary endpoint. So the trial was a prospective randomized controlled double-blind monocentric phase 2 trial using rapamycin during 1 year. We include patients with IBM following the Lloyd criteria. And as usual, I would say, we excluded patients unable to walk with all the normal criteria, I would say, not severe disease regarding the lung function, no kidney disease, severe kidney disease, no cancer, no seropositivity for HIV, and so on and so on and so forth, notably no cytopenia, because we will use rapamycin. So the primary endpoint, as I said, was the measure of the quadriceps strength using this device, the Biodex. The secondary endpoints were the safety, the other muscle group strengths measured by quantitative muscle testing, the 6-minute walking distance, the force vital capacity, 2 scales, and you will see which one, and the quality of the muscles assessed by quantitative MRI. We measure the fatty replacement of the muscles. So regarding the 2 scales, we use the IBM Weakness Composite Index, one index that I published some years ago with David Hilton-Jones in Oxford. So you have the details here if you want to see. And the IBM FRS that you all know. So regarding the inclusion in our files, in our registry, we can see almost 300 patients eligible. We excluded 240 patients because some of them, the majority, fulfill not the Lloyd's criteria. Some declined to participate. Some were too far from Paris. And that was at the time of the bimagrumab trial, and some were already enrolled in these second trials. So we included 45 patients. One we withdrew immediately. So we randomized 44 patients. 22 received the sirolimus. Sirolimus and rapamycin is exactly the same drug. 4 patients discontinued the treatment because of severe side effects, and 18 remains on sirolimus, and we performed the statistics on intention to treat on the 22 patients. Same things for the placebo group, where at the end we compare with the 22 patients under placebo. We included the patient quite rapidly. In fact, that is our experience, that the IBM patients are very keen to participate to the clinical trials. So that was really not a difficulty. And regarding the data, the results, you can see that there were no differences at the baseline between the 2 groups regarding the number of male and female, the age of the patients, 67, 66 in average, the 6-minute walking distance, the myometry, the measures, the force vital capacity, CK levels, etc. And regarding the results, it was disappointing, but the primary endpoint was not significantly different in the 2 groups, even if for every myometric measures, quantitative measures of the muscle strength, always the decline was more pronounced in the placebo group than in the rapamycin, but it never reached the statistic differences, maybe because of the lack of power of our study. Regarding the secondary outcomes, we can see one clear difference for the 6-minute walking distance with a flat curve under rapamycin, no decline, and a measurable decline for the in the placebo group. For the force vital capacity, that's the same. And for this HAQ, which is a scale of handicap, we can also see one statistical difference with one increase of the handicap in the placebo group, and it remains flat for the sirolimus group. Regarding IBM Weakness Composite Index or IBM FRS, maybe we have a trend. in favor of the sirolimus. So just a focus on the 6-minute walking distance. This is exactly the same data and the two way to represent it with the same p-value. And this is the median, here this is the average. Once again, the feeling is that under rapamycin, the patients are able to walk the same distance after 1 year, and it declines in the placebo group. Regarding the quantitative MRI, what we perform, in fact, the quantification of the fraction using the Dixon measure. We perform exactly the same measure at the same levels for every patient. And at the end of the day, we have a trend to have more fatty replacement in the placebo group in the legs of the patients compared to those who receive the sirolimus. And in the thigh, it is more significant this time with more fatty replacement in the placebo group than in the sirolimus. And we can observe some correlation, in fact, in the placebo group on the 22 patients between the 6-minute walking distance and the fatty replacement of the muscles. And this decline, as you can see, with a pretty good correlation, and nothing in the rapamycin group because there were no decline, obvious decline of the 6-minute walking distance and the fatty replacement. This is true in the legs, but also in the thigh. We perform the immunomonitoring of the PBMCs of the patients, and particularly of the CD8 cells. And once again, we can observe that one subpopulation of CD8 cells, the effector memory cells, decline under rapamycin after 1 year of treatment. And that time you can see a difference with the placebo group, where there is no difference over time of this subpopulation of cells under placebo. And this is one other subpopulation of CD8s, non-senescent this time. And here again, you can observe this time in the sirolimus group when correlation between these cells, the number of these cells, the decline of these cells, and the 6-minute walking distance, leading to things, even if the correlation factor are not very high, but it is significant, but leading to things that the more you have a decline of these cells, the more you preserve your 6-minute walking distance. And finally, the adverse events. So all were perfectly predictable because we know this molecule since 25 years, and we can observe more serious events in the sirolimus group. And in fact, 4 patients have to stop the treatment for severe mouth ulcers, aseptic pneumonia, renal insufficiency, and peripheral lower limb edema, the big one. And everything was reversible after treatment discontinuation. So you have here the list of the patients, of the side effects, and the number of times we can observe it, and in the number of patients. And in the placebo group, you can see that it was maybe a productive effect of the rapamycin. I remind you that the rapamycin is in the stent of that you put for the patients with infarction when you want to increase the diameter of the coronary arteries. And we can observe no arterio-occlusive disease in the lower limb or coronary heart disease in the rapamycin group, and some in the placebo group. Anyway, the most frequent side effect was canker sores, because we use the oral solution, the syrup of sirolimus, because it was easier to perform the placebo. And with this form, you can observe frequently these ulcers of the mouth, which is not the case with the pills. So the future is a phase 3. It is ongoing. It will start soon with our colleagues with 140 participants, including patients from Australia, and Merlin Nidam is the PI of this second trial, and also in America. And so I would like to thank particularly all the authors of the paper, and particularly Lisa Belin, who did the biostatistics, Jean-Yves Ogrel, who performed all the biometric measures, Pierre Carlier for the MRI, and Yves Allenbach, who is my colleagues and right arm. Thank you very much.
Thank you very much. This is very interesting. Any questions? We do have time for a few questions. Can you tell us a little bit about the criteria for the phase 3 are going to be the selection criteria or the inclusion criteria? Yeah. Are they going to be the same as the phase 2?
Oh, no. We move for the IBM-FRS as a primary endpoint. And we made the calculation of the number of patients based on the phase 2 trial.
So this is Rick. Why did you move to the IBM-FRS? I was going to ask that too. What was I know you didn't hit statistical significance, or there were trends in your phase 2 trial. So given that, what is the argument for going on with phase 3? Is it just that you thought you were underpowered, or your endpoint measurement wasn't accurate?
I think both, probably. Once again, we had in the team many discussions on the primary endpoint. I was for the 6-minute walking distance. And because of the ceiling effect, we thought that it might be a little bit risky. At the end of the day, the patients we included were in average at 16% of the quadriceps strength, 60% of the normal of their quadriceps strength. So they were in the interesting phase of the 6-minute walking distance with no ceiling effect at that level. So if we said at the very beginning that the primary endpoint was the 6-minute walking distance, then it will be a positive trial. Then regarding when you look at the standard deviation of the measures with the myometric different measures, clearly we can say that our trial has not the sufficient power. So I think, and then also we are not far from the significant results for the IBM-FRS. So after discussion with all the group, and because IBM-FRS is easy to perform, reliable and reproducible, then we decided to use this one rather than the 6-minute walking distance. Also because we have now the experience of the bimagrumab trial, where the 6-minute walking distance was the primary endpoint, but maybe the problem was here that it was not effective at all. So who knows? Yeah. But anyway, that's the reason why we use the IBM-FRS.
Excellent. Well, I really applaud your group for doing this. Mm-hmm. It makes a lot of sense. Matt Maragioli had this idea 20 years ago and just couldn't get it federally funded in the US. So congratulations.
Thank you.
Well, I would like to thank all the speakers for staying on time for these very stimulating talks. And I think we can go on a break right now.
All right. Are we on, Gil? Yes. All right. This is great. So I love this. When the music stops, you start dancing. So it's great to go into this next part of the MSG program. And this is having one of our MSG fellows present a science talk on their research. So just to frame the MSG fellowship, we started the MSG fellowship program a number of years ago in collaboration with the American Brain Foundation, in which Dr. Griggs and Dr. Gordon Smith are heavily involved in, and the AAN. And through this program, the AAN-ABF provides 1/3 of the funding, and the MSG supports it with 2/3 of the funding. So it's a 2-year clinical translational research fellowship. It can be done, right after your ABPN type fellowship and extending your fellowship 2 years, or it can be done as a junior faculty. And it's primarily aimed at clinicians doing research. It's ideally in the US, as I said, it would follow the APN neuromuscular fellowship. But we've talked about, we haven't had one yet, having a European trainee as well obtain one of these. So the applications open up on July 1st every year with an October 1 deadline. So the applications are due today, and we review them in December. And then we'll let people know who the winner is in January. So it's my pleasure today to introduce Dr. Paloma Gonzalez Perez, who is currently one of our MSG fellows. And Dr. Gonzalez Perez is a neuromuscular neurologist at Mass General Hospital. She obtained her MD at the University of Navarra in Spain and completed neurology residency at University Hospital in Seville in Spain. Her hometown, which is her hometown. And then she went to the University of Iowa to do further residency training. And she did a Partners Neuromuscular Fellowship at Brigham and Williams and MGH, which some of the mentors are on the MSG today, Dr. Amato, Dr. David, and others. And then she obtained her PhD in genetics of ALS with Dr. Bob Brown at UMass. She was a recipient of an NINDS R25 and is currently our fellow. So it's a pleasure, Dr. Gonzalez Perez, to introduce you as you give your talk on molecular biomarkers of myotonic dystrophy type 2.
Thank you. Good morning. Do you hear me?
Yes.
Yes, and my screen is shared
yes.
properly?
Yes.
Very good.
Yes.
Well, thank you so much for the introduction and good morning. I'm going to present our progress in this project, molecular biomarkers in myotonic dystrophy type 2. As a very brief introduction, you know that myotonic dystrophy type 2 is caused by a tetranucleotide expansion within the intron 1 of CMPP gene. And this expanded DNA transcribes into expanded mRNA that accumulates in the nuclei of the cells, forming what we call the RNA foci. So these RNA foci interfere with very important splicing protein regulators that don't work well because they are sequestered in these foci. So as a result, we have a subset of not normally spliced mRNAs that encode abnormal proteins. So currently, the best molecular biomarkers that we have in myotonic dystrophy type 2 and also in myotonic dystrophy type 1 is this specific subset of abnormally spliced mRNA in muscle tissue. But we know that muscle biopsy is invasive, that we don't need muscle biopsy to establish a diagnosis in these patients for the most part, and it's going to be difficult to clinically validate these molecular biomarkers in longitudinal studies using muscle biopsy because we will have to repeat them. And also we know that this disease is multi-organ, doesn't only affect the skeletal muscle, but other organs. So maybe just looking the muscle is not going to be enough. So we are investigating other type of biomarkers, such as the extracellular vesicles, to see if they can help us to find molecular biomarkers in a non-invasive way. So these extracellular vesicles, I have represented them here in yellow. They are in human biofluids, in urine and serum, and they contain different molecules, including mRNAs. And for example, right now in clinic, in oncology mainly, these specifics mRNAs are currently used as diagnostic and prognostic biomarkers for a specific type of cancer. So what Wheeler's lab did in 2018, they published that the same subset of abnormally spliced mRNAs that were found years prior in muscle tissue of myotonic dystrophy patients, he found that these extracellular vesicles in the urine and the serum of myotonic dystrophy 1 patients also contain this subset of abnormally spliced mRNAs. So the aims for my project is basically using the same methodology in myotonic dystrophy type 2. So we want to see isolate the extracellular vesicles in urine and blood of patients with myotonic dystrophy type 2 and see if these 10 splice variants that were upregulated or downregulated in muscle tissue and also in DM1 extracellular vesicles have the same changes in myotonic dystrophy type 2 patients. We also want to know changes in the expression of CMVP because it's where the mutation in these patients are located, and also by doing RNA-seq to see if we can identify other abnormally spliced mRNAs that maybe we are not aware of at this time. And then the second aim basically will be, once we have the transcriptomic changes, see if we can find any association with the clinical parameters, not only muscle weakness or myotonia, but other clinical parameters that these patients have. So, so far we have recruited 16 patients. I have tried to summarize a little bit the clinical characteristics of these patients here. You can see the age there, sex, basically the ratio female-male is almost 1-to-1. Most of them had muscle weakness at the time of sample collection. You can see also 50% of them had myotonia. This is at the time of sample collection. We know that the myotonia varies from visit to visit. 3 of them had heart problems, 2 of them with pacemaker. And then one thing that I'm very interested to follow, and also because of the role of these xRNA as prognostic and diagnostic biomarkers in myotonic, in cancer, and also because we know that at least patients with myotonic dystrophy type 1 has an increased risk for malignancy than general population. So one other thing that we are following with our patients is if they have been diagnosed with cancer. So that's why you see that column there, like prostate cancer, breast cancer, renal mass, we don't know what type, melanoma, and then 2 benign tumors there for 2 other patients. Then we do MOCA to see cognitive impairment in these patients. You can see there 5 patients had a significant low score on the MOCA scale. And then in the fatigue and daytime sleepiness scale, you see that at least 4 patients scored quite high. And then 3 patients were diagnosed formally with sleep apnea. So these are the patients that we have already recruited and we have samples from. So this is just a retrospective analysis that I did in our cohort. These are patients that have been seen in the Mass General Brigham system, so Brigham Women's Hospital and MGH over the years with myotonic dystrophy type 2. And I was just curious to see the frequency of cancer in this patient. Obviously, the most of them didn't have any cancer. This is a retrospective study, so there is a lot of limitation there. But 30% of them had at least 1 cancer, and 9% of them had more than 1 cancer, and some of the patients actually had 3 cancers. So when we see the type of cancers, actually there is no specific cancer that is more frequent than the others. Maybe skin cancers are more frequent than the others, but actually there is no specific other cancer that we can think it's more frequent in this population. So this is just something that we are following. So these are our 16 patients. You can see that for some of them, I mean, the yellow square means like we got urine from them. And then you can see that for some of them, we also got blood. We don't plan to do blood and urine in all the patients. From the study that Wheeler's lab did in 2018, we know that when we analyze the transcriptomic changes in blood, actually doesn't add much to what we find in urine. So we are just collecting blood in some patients just to do like a pilot have some pilot data and continue, maybe confirm that what we find in urine is the same as what we find in blood. So you can see there that we have 6 blood samples from 6 different patients. And you can see also that in the last year, in 2020, 2021, since I have this fellowship, so we have recruited 11 out of these 16 patients. And 2 of these patients came to clinic twice, so they gave urine twice. And also there are 2 patients that are following clinic since 2016. So also they provide urine sample every time they come to clinic. They are participating now for a few years too. So in terms of how many samples, right, we need to detect significant differences or to detect differences. So based again on the prior study that was done in myotonic dystrophy type 1 and choosing one of these transcripts, MBNL1, we will need a sample of 17 patients with DM2 and 17 controls to detect a 30% difference with a power of 80% and 0.05 significance level. So we are quite confident that we're going to get this number. We have already 16. We have some patients scheduled also to recruit, and some family members of these patients have expressed interest in participating in this study. So so we are quite confident that we are going to have over 20 patients by the end of the year. So this slide, from a practical point of view, this is basically what I do. This slide is a little bit busy. So basically, when we get the serum or the urine, we do a first centrifugation to get rid of the cells that we are not interested in. So we continue with this supernatant. And then we do an ultracentrifugation to pull down all the extracellular vesicles here at the bottom. And then from here, we extract the RNA. So we have RNA from these 16 patients in the urine or in the blood. And right now, at this time, we have all the samples with the RNA extracted, and then we have to do bioanalyzer, which, to select those samples with better concentration and better quality to be sent for RNA-seq and see if we can find or identify new transcripts that maybe we are not aware of at this time that are different in patients than in controls. So I don't have data to show you for RNA-seq, but what I can show you is like the RNA that we have converted all part of it into cDNA, and we have done quantitative PCR, a droplet digital PCR, to look for a specific transcript. So these 10 transcripts that were upregulated or downregulated in muscle tissue, and also the CMVP transcript that actually we are very excited about. So these are some of the preliminary data that I have so far. So this is urine, extracellular vesicles, and patients with myotonic dystrophy type 2 with a number here of 10 patients with myotonic dystrophy type 2. I mean, we have 16, but the data for this quantitative PCR, what we have done so far in terms of quantitative PCR, is for 10 of them. And you can see here 5 transcripts, and these were upregulated or downregulated in the muscle tissue. So you can see that there are significant differences for these 5 transcripts when we compare with controls. And here is the serum. As I said, we have here like 4 and 5 patients for which we have data from, and 2 transcripts also that were also upregulated or downregulated in muscle tissue. And here you can see some statistical differences between myotonic dystrophy type 2 patients and unaffected controls. So when we come to this table that I like, because here I summarize, you see here all the transcripts. These are the 10 transcripts that were published in 2013 by Nakamori and colleagues, very nice paper in myotonic dystrophy type 1 and myotonic dystrophy type 2 in muscle tissue. And you can see if the transcript was upregulated or downregulated in the muscle tissue of these patients. So, and then there are 2 other papers that also study some of these transcripts and confirm the same findings in muscle tissue as Nakamori and colleagues. So then in 2018, Wheeler's lab did identify this transcript in the extracellular vesicles in the urine in 40 patients with myotonic dystrophy type 1. And then this is what we are doing right now. In myotonic dystrophy type 2, we have data for 10 patients in urine and 4 or 5 patients in serum. And then the interesting thing is like we continue to see the same direction in the change of the transcriptomic, in the expression of the transcriptomic form in all the transcript. For example, the inclusion of exon 11 for the insulin receptor is downregulated in muscle tissue, but also in EVs of myotonic dystrophy type 1 and also myotonic dystrophy type 2. And this is the CMVP. So we know from prior publications that the CMVP mRNA transcript containing the expansion in intron 1 is upregulated intracellularly in muscle tissue, in frontal cortex, and in lymphoblastoid cells. So this is inside the cells. So our question is, well, how this looks in the EVs. And because it is difficult to amplify an expansion like this, so we said, okay, let's do the PCR for the normal form and see if we detect differences in the EV. So basically a forward primer, a reverse primer, and a probe here that spans across the splice size of exon 1 and exon 2. So we are not going to detect any expansion here. So, and this is what we continue. Last year, I showed a few data about this. Now we have more patients. I think here we have 9 patients. And then you can see that there are some, continue to be a statistical difference between myotonic dystrophy type 2 patients and unaffected controls. So we are very excited about this result because it's very easy to get in urine samples of the patients. And with this, I want to say thank you to the patients and families, everybody in Wheeler's lab, and everybody in the clinic, and our collaborators at Brigham Women's Hospital, Dr. Amato, Dr. Doughty, at Beth Israel, Dr. Rutkov, Dr. Darras at Boston Children's Hospital, Myotonic Dystrophy Foundation, and also the funding, Muscle Study Group, AAN, and ABF. Thank you very much.
Thank you, Dr. Gonzalez-Perez, for that great presentation. I love hearing from the next generation of neurologists who need to take over from me and Dr. Griggs and others. This is just great. And this is the type of work that needs to be done at universities before we make do a handoff for our industry partners to come up with new therapies. So thank you so much. I think we're just going to go on to the next section just because we're out of time. And I didn't see a question in the chat room. So thank you again. And stay in touch with the MSG, even after you're not an MSG fellow anymore. All right. Now I'm going to turn it over to James Lilliker from Manchester, who's going to be the MC for the next section of the program.
Yeah, hi everyone. It's a pleasure to be here. James Lilliker, neurologist from Manchester, just moderating the rest of the session here. And I'll hand over quickly to Colin Quinn, who's talking about a novel PET ligand in IBM. Colin, I think I saw you there.
Here I am, yes, thanks so much. I'm just going to try to share my screen and try to share the correct screen. Are we seeing the right thing? Let's see.
It's coming. Yeah, that looks right.
Perfect. So thanks so much for the opportunity to speak with you. This is a flash talk, so it's going to go fast, but also people did a lot of the heavy lifting talking about IBM earlier this morning, so I can click through the early slides quickly. So this was a collaborative effort, both within Penn Medicine, between neurology and radiology. Imaginib, who makes this PET ligand that we're interested in, and was the sponsor for the study, and Abcuro, a company founded by Steve Greenberg, interested in aiming at cytotoxic T cells as a therapeutic approach. So we're looking at a pilot study of CD8 PET imaging using this new tracer, which I will not try to pronounce, in patients with inclusion body myositis. So I'm going to kind of skip over this slide. We've already talked about the clinical features of IBM. I will say for a rare disease, I see an awful lot of it, and I'm sure you do too. So I think it's a worthy target, and there are no disease modifying therapies yet, despite the hard work of people who were talking earlier today in IBM. And I will also kind of go through the pathological features. We're really focused on this endomysial infiltrate that we see, and very specifically the CD8 cytotoxic T cells that are seen have been identified for a long time in IBM. So imaging has been used as a biomarker in IBM for quite some time, but there hasn't been anything that's used as specific immunologic marker. So, we say something has inflammation, but this is really trying to get at, the CD8 cells themselves. So this is a zirconium labeled human mini body. So it's an antibody that's been kind of truncated that has a high affinity for the CD8 glycoprotein. It's recently been used, so this paper is from a month ago, and the lead author, Dr. Farwell, is here at Penn, and looking at whether or not you can use this tracer in metastatic solid tumors. And really this could be interesting for immune therapies and checkpoint inhibitors, and looking at whether or not people are having a therapeutic response when you see these CD8 cells in their tumors. So we think that CD8, cytotoxic CD8 cells play a role in IBM. We've heard multiple people talk this morning about therapies that are aimed at T cells. This ABC008 is an Abcuro product. And so we think it would be desirable to be able to non-invasively measure the distribution of muscle within IBM patients. Of course, we want to make sure it's safe. We have no real reason to think it wouldn't be safe. But then we want to look at, can we detect, when we started this project, no one had ever been scanned before this way. So we actually weren't sure if we were just going to see nothing or what was going to happen. So this was an interesting way to proceed. So we used probable or clinico-pathologically defined IBM by ENMC criteria. We wanted people who could walk just to make sure there wasn't too much atrophy, although we'll talk about that. You couldn't be on immune therapy. I basically did a screening evaluation and tested strength and did an IBM FRS within a month of people getting imaged. The subjects received a single dose of the tracer. Now, we had a plan to kind of dose escalate, but it turned out that the images were quite good at the lowest dose, so we actually decided to keep the dose quite low. The comparator population was this oncology population that I was already talking about. And we selected 5 patients who got a similar dose to the patients in the subjects in the IBM study and were a similar age. So we have to do a little bit of PET parlance here, right? So the language of PET is the standard uptake value. That's a measure of PET tracer intensity. And I'm going to show you basically multiple ways that we look at this. We were really, when you do quantitative measures, focused on looking at a volume of interest, which is basically a sphere of a certain size, and you take the intensity of tracer within that sphere, and you can use different things, maximum. We used mean, which is actually the most kind of conservative way of doing it, so you don't just select some peak. So first off, 6 patients consented for the study. One subject signed the consent, went home, and then said, I don't want a PET. I'm too nervous. I'm claustrophobic. I don't want to be in the scanner. So he was out. Another person got the tracer and then went home, and it's 24 hours later that they're supposed to get the scan, and he fell and didn't get his scan. I don't think that was the tracer. I think that's an unfortunate consequence of having IBM. As we all know, these patients fall, and that disrupted his day, and he didn't get the scan that he needed. So that left us with 4 valuable IBM subjects. Here they are, all 4 of them. Now you'll notice some interesting trends and an outlier, right? So the patients are older. 3 out of the 4 of them have 10 years of disease, which is kind of interesting. Like, well, what are we going to see in people who've had disease for so long? One of them is very short duration disease. Actually, technically wouldn't meet criteria because he doesn't have greater than a year, but his pattern was fairly classic, and I was quite interested in trying to get someone in the early stages. You can see that he has a higher IBM FRS, and I kind of made up this MRC sum score. I mean, it was a 10-point scale, which has been done before, but the muscles I chose were somewhat IBM specific. And you can see that he's got the highest score. So these are maximum intensity projection images. And I feel like when you first look at this, what happens is your eye goes right to these black organs, and it just looks like a kind of black and white mess. So I would encourage you to look to the right of the screen. And what you can see when you compare the IBM and the cancer patient, if you look out at the limbs, the upper extremity and thighs, and you'll notice the oncology patients, unfortunately, are cut off right above the knee. So we don't get data to compare there. but it's much more gray in the muscle of the IBM patient. And so with that in mind, if you go back to the smaller images, you can see that that's true for basically all of the IBM patients we scanned relative to what you're getting in the cancer patients. So this is an overall coronal PET image. But then you can look at a fused PET image with CT images. And this allows you to look at specific muscles and kind of know exactly which muscles are affected, and also within a muscle. And I think some of the interesting findings here, so this is just a representative, a series of axial slices from one subject. And it shows that even in muscles where there was fatty replacements, in other sections of the muscle, we'd see fantastic uptake of the tracer. So this suggests that the CD8 T cell infiltration is part of the pathophysiology, even late, and that we can see it. So here's a more quantitative approach. So now we're taking that volume of interest, we're looking at the SUV mean, and we're comparing the IBM subjects to the cancer subjects. And kind of what you expect, the quadriceps, the humeral muscles, the finger flexors show very significant differences. Now, admittedly, the mean SUV here is lower than what you would see, say, in a tumor, where you've got very, very high concentrations of CD8 cells. But it's often a 2 to 3-fold difference between the oncology patients and the IBM subjects here. So something where we do think we could detect kind of normal from abnormal and potentially detect a change if you were trying to use a therapeutic. So just because there's so few subjects, you could say like, well, maybe we should just break it down and look by individuals. And that's what this is, right? So you'll see that not every subject uptakes in every muscle consistently, kind of as you'd expect. It's a little scattered, but generally speaking, you can see that there's substantial increases in tracer uptake in muscles that you care about. I realize it's a little hard to see the bottom, but basically it's the 4 subjects and the oncology patient is the light blue. It's just one selected oncology patient to compare to. So this tracer appeared safe and well tolerated. We are pretty sure we can see the tracer uptake in the IBM patients when compared to this oncology population. We saw it in even patients who had very late disease. So this could be a valuable tool, although I think obviously significant work has to be done to figure out exactly how we want to use this. It could be a biomarker for diagnosis, although admittedly, I often don't find imaging biomarkers that helpful. This is often a disease that's pretty easy to diagnose based upon the clinical phenotype. But in therapeutic development, especially early phase, when you have a small number of subjects and you're just trying to figure out, if I'm targeting CD8 cells, do I successfully get them out of the muscle? It might be very useful there. So thank you all for the time to talk with you. I really appreciate it. I'm happy to take any questions.
Thanks very much, Colin. That's really interesting. Really interesting work, especially given what's going on in the IBM field now, and this link with the CD8 cytotoxic T cells. What this tracer? You said. They have it and they go home and the scans the next day. Has it got a very long half-life? And what's the sort of radiation exposure associated with it?
Yeah, so the issue isn't actually the tracer there. It's the fact that the tracer has to get to the target. And it takes that 24-hour period to get the tracer to target. Interestingly, the tracer actually kind of permanently attaches. So you could scan them actually later. In the oncology population, they have looked at like scanning them further out than 24 hours. We kind of wanted it close together, just, I don't know, to keep things simple. But, like a normal PET tracer, you might do like an hour later, which would be way more convenient because the patient doesn't go home and fall and miss their scan as we experience here.
Any other questions for Colin from the floor? So I'm assuming there's plans to integrate this into some clinical trial work in the future?
Yeah, so I'm not in control of those plans. We've had some discussions about trying to do another project outside of a clinical trial, but I certainly think that it would be interesting to see it in an early phase trial where you're using it as a kind of go, no go kind of biomarker.
Yeah. Well, thanks very much. I think it's really interesting, to combine not just the anatomical imaging, but then almost this sort of functional and pathological sort of imaging. We can actually see the disease going on in front of our eyes on the scans you were showing there. So that's fascinating. Oh, a quick point from Tom Lloyd just on the chat before we move on. Would be interesting to see the effect of prednisone on the scan. Any comments?
Yeah, so I'm so glad you said that, because I've had this discussion with Steve that, if prednisone reduced your CD8, right, does that mean that this is actually not that useful, because anything that generically reduces your CD8 level doesn't necessarily have a functional impact? Or does it mean, the data that against prednisone actually isn't that strong, and maybe we've missed a therapeutic effect? So I've thought the same thing, that it would be interesting. I think you could do a fairly short course of prednisone, right? So you reduced your toxic exposure, and look at, did it reduce CD8 within the muscle?
Brilliant. Thank you very much. And with that, we shall move on to Amir Subiri, who's going to be talking about the 10-PS mnemonic for the diagnosis of IAM. Are you there, Amir?
Yes, I am.
Hi.
Can you guys hear me?
I can hear you. Would you like to share your slides?
Yes, just give me 1 second. Can you guys see my first slide?
You just need to activate the power. Yes, excellent. 10Ps.
Okay.
That makes more sense. Thanks, Amir.
All right, thank you. Thank you for giving me the opportunity to present our approach to diagnosis and management of idiopathic inflammatory myopathies. There will be a changing in the gear here to completely clinical. So the objective of this talk is to introduce a novel multidisciplinary diagnostic approach to IAM, and the outline is I will explain the 10Ps mnemonic and a representative case. How does it work? As you all know, the most widely known criteria for the diagnosis of IIM is Bohan and Peter, which was developed more than 40 years ago. And basically, it uses only 5 defined criteria of like clinical exam weakness, serum CK or muscle enzyme, EMG, muscle inflammation. And if there is characteristic skin rash, it's called dermatomyositis. And if there is no characteristic skin rash, is polymyositis. There are, however, some major issues with the Bohan and Peter criteria, and as explained today and earlier. So there has been several new clinical entities like IBM, IMNM, and anti-synthetase syndrome, which are not considered. There has been major advances in the diagnosis of IIM, including muscle-specific antibodies and pathology, which are not very considered here. And the polymyositis is a very rare disease and maybe heterogeneous. Some experts even call it unicorn, maybe. And then lastly, dermatomyositis may have uncharacteristic skin rash or maybe no skin rash. And that also true for the, EULAR ACR 2017, criteria as well, most of these. So currently the approach to diagnosis or definition of the IIM is basically similar to, elephant in the dark, based on the background education of different subspecialists involved in the care of these patients. So recently we published a review paper in Practical Neurology, which is co-authored by Dr. Lisa Christopher Stein. This slide basically developed by her and adopted by a paper published initially by Dr. Benveniste. As explained today, there are 4 major subtypes of the IIM, including overlap myositis, dermatomyositis, IMNM, and inclusion body myositis. So what is, we already discussed about like ILD and malignancy. However, this slide shows the most advanced, the development in the care of these patients, including the myositis associated with calcinosis, and these gold stars shows those amyopathic dermatomyositis and also associated with, the cardiac conditions and malignancy, etc. So we developed a 10P models, which basically can apply all of the points that mentioned in the prior slide. I initially actually adopted and learned these like 10P models from Dr. Jim Dick from a prior meeting, which was chaired by Dr. Shafiq Karam in Oregon Health Science Institute before COVID. And this is for 10P for myopathies. And that's it starts with 10P, like pattern, plasma. I will explain this in the next slide. Pathology, phenomena, picture, period, physiology, pills, pharmacology, and pedigree. So some of these are very self-explanatory, such as pattern, which is asymmetric versus there is distal versus axial. Period means how is the disease course, acute, subacute, chronic, or intermittent. Phenomena is very important and includes all of the extramuscular involvement like skin, lung, heart, weight loss, edema. There is a two-part which like pills and pharmacology. Pills means all of the toxins, and the pharmacology what I meant is that how the patient respond to treatment. Because, for example, as you all know, in like certain diseases like the dysferlinopathy, you may have most of the stuff here, but when they do not respond, then we go back and revise the diagnosis. Plasma is that everything we diagnose and detect in the plasma. Pathology and picture are self-explanatory. Say MRI, CT, physiology, pedigree means family history and genetics. So here is the slide, just a case vignette that I wanted to briefly mention and see how does this work. So we saw this lady, 61-year-old, early in 2021, who presented with falling and weakness in proximal, lower extremity, more than upper extremity, had difficulty running, getting in and out of the car. She lost 45 pounds. She thought that it was like weight loss, intentional. She did not have any other systemic condition, no diplopia, skin rash, heart condition, etc. There was no otherwise significant past medical history. She's not taking any medication, and she received Pfizer vaccine in late February. Her exam showed fairly severe weakness in proximal lower extremities, also had weakness in upper extremities, but she did not have any weakness in distal lower extremities. And her electrodiagnostic test showed irritable myopathy. Her CK was slightly elevated, maximum at 650, and otherwise, TSH, serum protein electrophoresis was normal. Her CBC is normal. However, when you look at the differential, at some point there was 30% of eosinophil, and her IgE was slightly elevated, and flow cytometry was negative. Did muscle MRI, which shows a T2 hyperintensity in vasti muscles only on the right side. And in muscle pathology, there is inflammation, which are perimesial, endomesial, and also perivascular. And there was perivascular atrophy, as you can see here. And there was a perivascular mitochondrial staining, COX negative, STH positive here. And there, interestingly, there were some eosinophil infiltration and granuloma. And in the staining for the MXA, myxoma virus resistant protein A, there was like some staining in the both sarcolemma and sarcoplasm of this patient. So myositis antibody panel was positive for NXP2, and all of the other myositis associated and myositis specific antibodies were negative. So malignancy workup was basically negative, showed some breast microcalcification, and then JAK2 mutation was negative. And cytogenetics was negative. So she was treated with 40 milligram daily prednisone and azathioprine, and she is responding to treatment. So going back to mnemonics, so the pattern was symmetric proximal in upper and lower extremity. Disease course developed in about a month, subacute. She doesn't have any other phenomena except, the weight loss I forgot to mention here, but microcalcification. She's not on any myotoxic agent. CK was slightly elevated, eosinophilia and positive NXP2. Pathology is consistent with dermatomyositis, actually. Picture shows asymmetric T2 enhancement in vasti muscles on the right side. Irritable myopathy was negative, didn't have family history for myositis, but and also negative JAK2 and pharmacology. She is responding to treatment. So the question is this a DM, PM, IIM, overlap myositis, or any other entity? So final diagnosis is this patient who has NXP2 positive dermatomyositis, sine dermatitis, and but interestingly, if we didn't have these thorough workup, this patient might have been diagnosed with polymyositis. Or maybe related to the vaccine. So eosinophilia and elevated IgE and granuloma are likely due to COVID vaccination. So the biopsy was performed actually on the same muscle. And considering annual cancer screening for 3 years and given increased 3 to 7 times cancer risk in this patient, we are considering repeating the cancer malignancy workup. So advantage of the 10P mnemonics approach versus the classic Bowen and Peter or EULAR ACR is that this is comprehensive. This provides very specific diagnosis, which is important, as you notice here, in that not only in the treatment but also prognosis. There is internal coherency. We want to see whether there is such coherency between all of the different findings here, able to detect atypical cases easily and quickly. For instance, in this case is about the eosinophilia and also the granuloma. And this uses a multidisciplinary and interdisciplinary approach. It uses the same languages between the different specialists and does not rely on any certain clinical or paraclinical test like antibody or pathology or MRI, etc., and avoid over testing. We don't have to do all of the tests in all of the cases. If they are running doc test, if the doc test is positive, then we don't have to run everything. And the combination of important P's is important in case. So final take-home message here is that the 10 P's mnemonic to acquired myopathies provide a comprehensive, multidisciplinary, specific, and cost-effective approach. Thank you very much for your attention, and please let me know if you have any question. And we have a monthly neuromuscular pathology case conferences at our institution, and if anybody interested, trainees, please contact me. Thank you.
Well, thanks, Amir. That's very interesting, and what sounds like quite a comprehensive way of assessing those patients and making sure that you've got the right diagnosis. Has there been any validation work performed?
No, not yet. Actually, we have started this about 3 years ago, and we have a very large number of the cases actually. So, but we are planning to do the validation, and it will be very interesting. We're excited to do that.
Any questions from the floor? I might just ask an unfair question then, Amir. Do you think polymyositis exists?
I think it does exist, but I think it's very, very rare.
I think that's a good answer.
Thank you.
Thank you very much.
Of course. Thank you.
Thank you. And we'll move on now to Eli Nadav, who has an interesting case series of patients with axial weakness associated with inflammatory myopathies. Eli, are you there? I can see you.
Yeah, hi. Thank you for the invitation. Let me share my PowerPoint. Oh, it doesn't look like that. Sorry for that. Here it is.
Yeah, that's right. Yeah.
All right.
We just need the slideshow view.
Yep.
Great. That's working.
All right. Just because of the...
Eli, we've gone to presenter view.
Okay, let me swap then. There we go.
That's it.
Okay, thank you. All right. So thank you for the invitation to present about the inflammatory myopathies presenting with axial weakness. Because of the flash presentation style, I will be focused on dropped head syndrome, but it's a very representative entity of axial myopathies in general. These are my financial disclosures, nothing really related to today's talk. So as a background, dropped head syndrome can be due to underlying neck extension weakness or dystonia, Therefore, it can be due to central nervous system disorders such as primary dystonia or Parkinsonian disorders, but also can be due to peripheral nervous system disorders. Anyway, along the motor pathways can result in dropped head syndrome. Probably people are most familiar with a neuromuscular transmission defect such as myasthenia gravis or motor neuron disease such as ALS. Very, very rarely a neuropathic process. But when it's a myopathy, it usually poses significant diagnostic challenges. And this is for several reasons. One, there's limited available literature to guide the diagnostic workup. And there's limited access to axial muscle biopsy, which is sometimes needed in these cases, and some concerns about interpreting such biopsies by muscle pathologists. Unfamiliarity of physicians with the different types of myopathies that can present with dropped head syndrome, and also a common presumption that myopathic dropped head syndrome is frequently associated with an untreatable non-specific myopathy. So to fill in this gap in the literature, we published this paper last year in Neuromuscular Disorders with Dr. Al-Hamad, who was our fellow, to identify the various hereditary and acquired myopathies where head drop can be the presenting or predominant feature of the myopathy. And it's a retrospective chart review of the electronic medical records at Mayo Clinic. And to be included, patients had to have a conferred myopathy, and the dropped head syndrome had to be the first or the predominant manifestation of the myopathy at onset. What do we mean by predominant? That the patient had to be able to ambulate independently without any assistance or device at time of development of the head drop. With that, we identified 107 patients and established either histopathological or clinical diagnosis was reached in about half of them, 57 patients. As you see, they're a little bit older patient with a median age of 68 and slight male predominance. The head drop duration, or in other terms, the delay in diagnosis, was on average about a year, but up to 20 years in one of the cases. The patient where a diagnosis was not reached, as you can see here, only 29 of them had a muscle biopsy. So to focus on the inflammatory myopathy, first, this is the spectrum of clinical and histopathological entities that were represented in the 57 patients that had a diagnosis. And here we went by histopathology. So inflammatory myopathies or myopathies with inflammation on muscle biopsy, we had 16 patients. We had another common immune-mediated entity in this cohort, which is sporadic late onset nemaline myopathy, that's characterized by the accumulation of nemaline rods in atrophic fibers. Additional immune-mediated myopathy, we had 2 patients with inclusion body myositis, 2 patients with scleroderma myopathy. Now, these are 2 patients that did not have inflammation on biopsy, otherwise they would have been there, and a single case of necrotizing autoimmune myopathy. So I'll just be focusing on these immune-mediated myopathies in the rest of the talk. So just a few things here. Although these patients are referred for isolated neck weakness, after doing a thorough motor examination, only a minority of them really had weakness only in neck extension. And I would like also to point out, due to the proximity to respiratory and bulbar muscle, respiratory and swallowing difficulties were relatively common. So now in the category of inflammatory myopathies, if you recall, it included 16 patients. About half of them didn't fall into a diagnostic category. There were 2 patients with scleroderma myositis, and there were 2 without myositis, just scleroderma and a myopathy, so 4 with scleroderma. 2 patients with autoaggressive feature, if you wish to call them polymyositis, that's fine. 2 patients with granulomatous myopathy, one of them had sarcoidosis, a single patient with dermatomyositis, and 1 with graft versus host disease. As far as laboratory characteristics, just a couple points here. As Dr. Agarwal mentioned, creatine kinase level is really not the best diagnostic or outcome markers in this patient and was elevated in only 22% of the cases. As a monoclonal gammopathy in the serum is a good marker to raise suspicion for sporadic late onset nemaline myopathy, although it's not specific. For instance, about half of the patients with radiation-induced myopathy had a monoclonal protein. It's always IgG in slow. And last, also due to proximity to these muscle, bulbar and respiratory involvement is quite common, hence also the importance of establishing a diagnosis to just monitor comorbidities and provide care even if the entity identified may not be treatable. Briefly on muscle biopsy, overall here about 62% of axial muscle biopsies were diagnostic compared to 42% with limb biopsy. General rule, you want a muscle that's involved. If there's a limb muscle that's involved, you go after it. If not, then you will need a biopsy from axial muscles. Other muscles that we use, other than just the paraspinal, splenius capitis, trapezius, sternocleidomastoid, are, if they're involved, they would be good targets as well, and not as prone to the wear and tear concerns with the paraspinal muscles. Briefly about the treatment here, 43 patients were treated. There was no difference in the baseline characteristics between the patients that were treated versus not. As you see here, the numbers are small, so I would cautiously interpret the findings. But overall, patients with isolated neck extension or isolated axial weakness were equally represented in both groups, the group that responded to treatment versus not. For some reason, patients with neck flexion weakness were more common in the treatment responsive group, and patients that they reported, they felt as if their limbs are weak as well. So to conclude, the dropped head syndrome can be due to underlying immune-mediated, potentially treatable myopathy. And as you can see here, even with the immune-mediated part, the treatment really is variable from one entity to the other. So the choice of a treatment regimen will depend on the underlying diagnosis. Now, the decision to initiate empiric treatment for patients without a specific diagnosis or patient with myopathy with rimmed vacuole, which we did not cover today in this talk, should be decided on a case-by-case basis. But we recommend, just based on this series, considering a treatment trial at least in patients with subacute progression of the head drop, evidence of neck flexion weakness, evidence of a connective tissue and associated connective tissue disorder, especially scleroderma, where the biopsy may not necessarily show a myositis, markedly elevated creatine kinase level, or evidence of active graft versus host disease. Now, you may consider treatment in other patients as well, but just to highlight some of the indications for treatment. And that's all what I have, and I'm happy to take any questions. And I think there are a couple in the chat box.
Yeah, there's a couple. So from Mazen Damashki, the similar question actually from Michael Weiss as well. So in the IIM group, was there associated ILD? And then Michael's asking, in the IIM group, were there any patients with positive myositis associated autoantibodies?
So there was a single patient who was mildly weak Q antibodies, but none of the classic antibodies there. And as far as interstitial lung disease, I think that just one of the scleroderma had associated interstitial lung disease, but not the others.
And we have another question from Deborah Gilanis. Was intact PTH and vitamin D level checked on the patients?
Yes, all patients get a calcium screen usually, and I don't think we checked PTH on all of them, but calcium and vitamin D were checked.
And Gil Wolf is referring to some older literature on the subject, and Leo Wang is asking, what does responsive mean in the isolated neck extensor weakness patients? How did you judge their response, Ellie?
So the response in this case, given the retrospective, was improvement confirmed by neurological examination. For example, if it just was head drop, that the patient were able to keep their neck in the erect position without any collar or any particular effort to do so.
And Shafi Karam is asking, what would you consider to be a sufficient treatment trial? How long and how much? And what drug?
Yeah, that's a very good question and very difficult question from Shafiq. Well, as you see, these entities, the treatment of these entities is quite different from one on the other. basically, if I have a lot of high CK, like in the 1,000, that's usually a surrogate of muscle necrosis on muscle biopsy, we tend to go with IVIG rather than oral prednisone. It's just our practice, not that I'm saying any guidelines or anything. If there is a monoclonal protein, and even if I couldn't prove it's a sporadic late onset myopathy, I might also favor IVIG because prednisone would not work. Obviously, if it's IBM, I would not treat them. And the rest, just inflammatory myopathy, or if I couldn't find a specific cause, and I want to go with empiric treatment and considering cost and so on and so forth, oral prednisone would be reasonable. How long in general, before determining a patient is responsive or not, I usually treat for at least 2 months with any agent, 2 to 3 months before determining treatment response.
And I'd certainly, speaking to our pathologists about this, and when we've provided them with some, say, paraspinal muscle biopsies to analyze, they found it extremely difficult. I think it's quite technically challenging to even understand what's normal and what's abnormal. But I think you've given a sort of really useful overview of clinical pointers that we can use to help pick out those patients that might be treatment responsive. So thank you very much.
Yeah, sure. Just briefly about the paraspinal muscle. The problem is mostly with oxidative enzyme staining and fiber type grouping. But if you see IBM, if you see necrosis, a lot of mitochondrial dysfunction, I mean, wherever the source of the muscle is, even if it's an inner ear muscle, you would have your diagnosis with that. But I would just carefully interpret oxidative enzyme staining in paraspinals.
Sure. I'd like to take this opportunity really to thank all of our speakers this it's this evening where I am, but morning or afternoon, wherever you may be. And thank you for sticking to time. Thank you for the interaction from the audience and the questions. It was a really great session, and I certainly learned a lot, and I hope you did too. I'm getting a message from the organizer here saying that all sessions were recorded and will be available approximately 1 week after the meeting on the MSG YouTube channel, which I did not know existed, but that sounds fantastic. I'll definitely be subscribing. And all the links will be sent out. There are now some breakout rooms and some mingling rooms.
Yeah, can I just step in, James? And
yeah, sure.
With you. And James, thank you for emceeing that last great session. I think what we're seeing of the power of MSG is we can have invited speakers, we can have these flash presentations from our members, and then we can have these really cutting edge presentations from industry. And it's that mix which really makes this unique. So it's just tremendous. And I'm so glad to see there's so many people signed up today. So Dr. Hanna, I don't know if you're there. I see your name is still on there, but I think it's our job now to close this session and to send people to the mingling rooms. So
yeah, I am here.
Yeah, good. In the dark. It's dark there, right? Yeah.
Yeah. Yeah.
What do you think of that session, Dr. Hanna? Wasn't it great?
I thought it was brilliant. I thought the industry presentations were really interesting, actually, and potential for new therapies in Duchenne is obviously very exciting, and the delivery of the ASO looked very exciting. But I thought all the presentations, including the very clinical ones, were really excellent, actually. So to thank all the speakers for excellent presentations.